Will be okay. Hello, everybody. Dear distinguished speakers and participants, dear colleague, on behalf of the Brazil InterPore chapter, it's my great pleasure to welcome you in this second and last day of our fourth InterPore Brazilian chapter meeting. I'd like to thank all of you again from Brazil and abroad. So let me highlight a little bit our session of today. In the beginning, you have Professor Magi. He will say a few words about InterPore and highlight special actions geared towards diversity, in particular, more involvement of researchers from developed countries and gender equality, and mention about InterPore Academy and InterPore Foundation. In the second, we'll move to the section Porous Media and Neuroscience with chairs Gregorio Shapiro and Márcio Carvalho. We have four speakers: José Barbosa from Federal University of Pernambuco, Brazil; Paulo Couto from Federal University of Rio de Janeiro, Brazil; Hadi Bed from Delft University of Technology, and Yulia Petrova from St. Petersburg State University in Russia, and now is here in Brazil in a postdoc, excellent research visit position. So, Professor Marzid, the word is yours, please.
Thank you. And I want first to congratulate you and the whole Brazilian Brazilian chapter steering committee for organizing yet what seems to be a very successful meeting, both in terms of quality and quantity. And I want to thank you for giving me the opportunity to address the participants. Let me share my screen. Yeah. So I think you see my screen?
Yes.
Okay, great. Yeah, so I will, on behalf of InterPore, I want to say a few words. First part will be about ongoing activities where you all can play a role and have a share and form actually activities of InterPore and what InterPore is. And then I'll talk about diversity, equality, and inclusiveness efforts that InterPore is undertaking. So the first thing is about the InterPore Academy of Porous Media. As you know, this was established last year, and this is to really coordinate and concentrate activities of InterPore in areas of short courses, webinars, thematic workshops, public outreach, and young academy activities. So I'm not going to go into details of Academy. This was explained during the InterPore annual meeting. You can also read about it workshop. I would like to bring to your attention the upcoming short courses. Would be one on linear poroelasticity by Holger Stieb from Stuttgart University. It happens that actually all three upcoming speakers are from Stuttgart University. That is the end of September. Then in middle of October, I'll give a short course on transport of viruses and colloids in variably saturated porous media, where I'll talk about experimental and theoretical aspects of colloid transport and virus transport. And then free flow, porous media free flow coupling will be a short course given by Rainer Helmig in November. So you can find the information online under the Academy button of website of InterPore, and please feel free to go and explore it. And especially for students, there would be fee waiving possibilities. I would like to mention the InterPore Young Academy of Porous Media that is being co-chaired by Marcel Moura from Brazil, Norway, originally from Brazil, Catherine Spurin and Mohammad Nouraipour. They have various activities Among the most important is the Porous Media Tea Time Talk lectures they organize for, say, junior researchers. So volunteer to organize short courses or webinars, or propose subjects or propose lectures. Okay, I would also like to mention the album of Porous Media Structure and Dynamics. This is a collection of the state-of-the-art experimental and computational visualization images. This will be published as a hard copy book by Springer. There will be only images, no videos, but later on we want to make this an online feature also with videos, and we are hoping that we can provide financing via foundation, InterPore Foundation, to have this open access for at least for InterPore members. So you still have a couple of weeks to submit your contribution for publication in this album of Porous Media. I would like to bring to your attention the 2022 Kimberly-Clark Distinguished Lecturer, Professor Jack Huyghe from Ireland, originally from Belgium actually, and he's been working at University of Eindhoven too. He will give a lecture on poromechanics in extremely large deformation, swelling, and fracture. As you may know, Kimberly-Clark Distinguished Lecturer will be funded by Kimberly-Clark. So his travel expenses, if you invite him, will be paid by Kimberly-Clark through InterPore Foundation. And you only need to host him for 2 nights and 1 day for local expenses. You can apply online on InterPore websites. Now, I wanted to talk about diversity, equality, and inclusiveness. This has been an issue that actually from the beginning, InterPore has been very aware that we need to pay attention to it. We have always tried to consider in various areas of our activities the equality in gender, age, ethnicity, country of origin, subject areas, nationality, whatever, anything that determines the uniqueness of our members. We have really tried to address that, but recently this has been added as Article 8 of our bylaws, so that we are committed really to that. There is a committee that is foreseeing this, and so we are trying to, in recruiting members, allocating the invited speaker, clearing speaker slots for conferences, in co-organizers of workshop, awards, prizes, all of this. We really try to pay attention to diversity, equality, and inclusiveness. The specific efforts, actions that we have had is that we really have tried to increase the share of women members of our various committees, and also their participation in annual conferences and also annual honors and awards. There are, that's related to gender equality. For various nationalities and countries, we have provided conference grant for researchers from low and middle income countries that we hope to be able, by funding from InterPore Foundation, to upgrade it to travel grant, not just the conference registration fee, but also provide funding for travel grants to researchers from middle and low income countries. So please do apply for it when the time comes for a participation in the InterPore conference. We have a student travel grants for participation in InterPore meetings, with a special focus again for students from LMI countries, low and middle income countries. We have waiving fee possibilities for students for participation in short courses and workshops. The Reinfangen Early Award Carrier has preference for young researchers from LMI countries. And we have a special category of group membership for academic researchers that are associated with national chapters from LMI countries. This allows them to become member for as low as 15 euro per year. We also have the possibility that a national chapter becomes institutional member with 35 members paid with the fee of institutional member. That means they'll have a fee as low as 17 euro a month. And finally, we have created a task force for InterPore development in Africa, because we have noticed there are really very limited participation from Africa. So we want to facilitate the participation of African researchers in various InterPore activities and events. In order to also make it possible for anyone who has any complaints or any issues, concerns about the diversity and equality, there is a ombudsperson, is Professor Linda Abriola, Brown University, that you can write to her, ombudsperson@interpore.org, with any complaints that you have about also not only the DEI issues, but also any mistreatment or misconduct that is by any InterPore member or officer. Okay, at the end, I'd like to draw your attention to the upcoming InterPore annual meeting in Qingdao. We hope that it will be not only online, but also in person. We are very much anxious and excited to know what happens with the Corona development. We have good hopes that we will have at least limited participation in person from China, Asia, and maybe some European countries and the Americas. Okay, well, thank you very much for your attention. If there's any question, I'll be more than happy to answer.
So are there any questions for Majid, maybe? No?
No, looks like not. Okay.
Okay.
Well, thank you very much.
I'd like to thank, oh, sorry, Majid. Please go ahead.
Well, thank you very much for everything.
Oh, thanks, Majid, for your very nice review about InterPore activities. Here from Brazil, would like to thank you a lot for all support of InterPore, for realization of this meeting, for social media support about scientific directions, guidance. We hope to continue this collaboration with you and all the community.
Absolutely. Brazilian chapter is doing fantastic.
Oh,
good
many
luck
thanks.
with everything.
Eduardo, can I just add quickly in regards to Majid's notes?
Yes, please go ahead. Please go ahead.
No, I just want to mention that the Brazilian chapter has actually co-organized one of the sessions of the Tea Time Talks together with the InterPore Academy. So there is, I think there is more than that session. Actually, there are some 4 young speakers from Brazil that have talks available on YouTube. And I'll just put the link for that on the chat here. So if anyone's interested, you can check that out later.
Excellent.
Okay.
Oh, many thanks, Marcel. We can provide also additional link in our website to this conference.
That's great.
Oh, many thanks.
I'll copy it down on the chat. Thank you.
Oh, many thanks. So, Gregory, Marcio, please, Marcio Carvalho, go ahead.
Okay, thank you, Eduardo. Thank you, Majid, for starting the session today. So I'm Marcio Carvalho. I'll be chairing this session together with Gregory Shapiro. The section will be on porous media and oil science. So I'll go ahead and start. The first talk is going to be by Professor José Antônio Barbosa from the Federal University of Pernambuco. José Antônio, you have the floor, or you have the screen now.
Okay. You can see the presentation?
Yes.
Okay. And my name is Antônio Barbosa, José Antônio Barbosa, and I'm a professor at the Federal University of Pernambuco. I work in the Department of Geology, and I have background. My background is in sedimentary geology and reservoir characterization, and I want to thank the organizing committee to having me for this presentation. I'm glad to give this talk today, this excellent audience, and thinking of what the committee recommended about how to bring some information that can make interest for young researchers about the issues we have developing these techniques and methods for reservoir characterization involving the description and the questions that we have with the Porous system. I decided to talk about some work we have together with some colleagues here in the Department of Civil Engineering and the Mechanical Engineering, working with development of geological characterization and numerical simulation of reservoirs. And my idea is to discuss some questions about the classical description of porous systems in the reservoir characterization from geological point of view, if I can say that. And then to describe some questions we have, I have a great opportunity to work with these colleagues from the engineering, many engineering areas that work with reservoir characterization, and it gives us the opportunity to connect some information, some problems that we share together, and that we try to solve together. And this gives us some point of view, some insights about the problems we have. And I will share some of these 2 points that I think it's interesting to bring some researchers some interest to work. And my expertise is in stratigraphy, sedimentology, areas of sedimentary geology, diagenes of carbonate rocks, and seismic stratigraphy and reservoir characterization. And thinking about the classical description, what we teach to geology students in general about porous systems, what is permeability and porosity in sedimentary rocks. We face this classical interpretation of the solid and the void spaces that we have in the solid that can be connected and that can be used to transport the fluids. And this conception, as I will advance in the presentation, was systematically improved and changed in ways, in very interesting ways due to the challenge that the geology faced to match the questions and the problems for the new, as I can say, geological description of the reservoirs in the modern area of the industry. In most of the conceptions we have here, we have sandstone, a coarse-grained rock, a granular rock. And most of the descriptions we use or the conception we have about these porous systems is related to the beginning of the oil industry development. We, in the many decades in the beginning of the oil industry, we have mapped and we have exploited reservoirs with good quality related to rocks with determined characteristics. And many of these rocks, these reservoirs, are composed of granular rocks. And most of the understanding in this many decades in the beginning of the history of the oil industry shaped these concepts, this interpretation of we have a description, macroscopic sample and micrography of sandstone, and we can have this conception of the solid matrix formed by grains and cementing between the grains with chlamine minerals and the cementing which forms from the fluid that is involved that is mixed with the grains during the deposition. And we used to study the effects of the burial, which can teach us about the effects that reduces porosity and affects also permeability, the compaction and the chemical reactions that occurs with the increasing in temperature and pressure. And normally for granular rocks, we have a good understanding what normally occurs. And we have including many studies and with the normal understanding that we have now about these processes, we have codes that can give us a simulation about the compaction that some rocks experience during the burial. And this was interesting, and this was entire universe of information for granular and class rocks formed by grains of silicate minerals and coarse grains to medium grained rocks and fine grained rocks. But for carbonates, the evolution during the burial can present some difficult process to reconstruct, to understand, and most of the porosity in grained rocks, in granular rocks, are present during the beginning of the burial, and that it will experience the reduction of the porosity and the influence of this reduction in permeability during the burial process. And in carbonates, we have primary porosity. Normally, carbonates are compact. The matrix used to be a compact material formed by biogenic grains and carbonate minerals like dolomite or calcite formed in aragonite. And most of the interesting porosity is formed during deep events of burial with the formation of fracturing and dissolution. And this brings different problems and questions, and that geology has treated for a long period. And some of you will think a little boring to observe these figures showing the classical concept we have about the granular rocks with the description of pores and the codes that connect pores and the questions involving the relation between fluids and mineral matrix. And this is what we normally teach to students in geology, and we can see some of these processes in experiments. But now we have questions involving the description or the understanding of porous systems, of course, with implications for permeability and transport of fluid that are very different and in scale and in the conception. Of course, the process of understanding the geometry of the porous system, how it's connected, how the shape of the pores, the class of the pores, and we have also some understanding, basic understanding of this for granular rocks. Most of the concepts in the classical description are based on this classical understanding of granular rocks, and not so involving problems like fracturing or the influence of fractures. And we have some questions that are really easy to see when, for example, we can use to correlate for the same rocks in different depths of burial. How is the relation between permeability and porosity? And we have, for example, granulated rocks, coarse grained rocks, and fine grained rocks. We have some information that can bring us some estimates interesting estimate how the rock how some class of rock will comport will behave in a defined depth of burial. But for carbonates, it's not so easy, because when we have fracturing and also the percolation of fluids, hydrothermal fluids, and fluids from the surface that can access these rocks in shallow conditions, we have it's difficult to relate depth of burial with the influence in the alteration of porosity and permeability. So things, as we move along the decades, and we reached a situation where the most of the good quality reservoirs were mapped and exploited, developed. We need to go deeper. We need to go to the offshore regions, and this had brought some new challenges and problems. Most of you are aware of that. And for example, now we teach to the students what is the classical petroleum system, which involves sedimentary rocks, a classic description of how sedimentary rocks forms the elements of the petroleum system, like classic rocks. Fine-grained rocks will be the seal, and other granular rocks or carbonates could be the reservoir if it is if the porosity is present with the good permeability. For example, igneous rocks and metamorph rocks was not counted as possible reservoirs, and if it's fractured, or if it has some vesicles or extremely dissolution, it could be treated like in some cases fractured basement rocks, crystalline rocks are treated, are developed as reservoirs, but it is like some exotic cases, not the classical reservoir formed by sedimentary rocks that we used to treat. So things changed as the conventional resource became scarce, and we need to move to the easy part ended, and the easy resource and the easy volume resource has come to an end. And so we need to move to the worst cases and the difficult case. So this is one example of an estimate, of course, based on the price of the commodity and the availability of technology. But it shows that today we have exploited the granular rocks and the reservoir-based granular rocks, and to move to carbonates and more. And now we have large quantities of the remaining conventional oil in carbonates, and also not so conventional transitional, and like the carbonates in deep waters and ultra deep waters, what brings new challenges. And the remaining reserves, considering regarding the conventional system, conventional classes of reservoirs, we have these in carbonates. So we in the last 2 decades, most of the research was devoted to understanding, to better understanding in treat and deal with the problems involving carbonate rocks. And another thing happens, of course, the industry moved the unconventional system. In terms of geology, it is like a new, a complete new petroleum system. Now we treat source rocks like reservoirs, in the case of shales, of course, you're aware of that, and tight rocks with very low porosity. The fluid is dispersed, it's not concentrated, it's not forming saturated fluids in hydrocarbons, and we don't have well-defined limits of the better concentrations in some cases, like tight reservoirs or in shale or in other types of fine-grained rocks. And so this brings new levels of problems, of the questions that geology tried to match and to solve as time passed. One example of that, just for consideration, we have, for example, an electron microscopy image showing a good reservoir, a good quality reservoir, sandstone, a grained granular rock with almost no clean minerals, no cement, with good pores, and you can see, and the throats connecting the pores, which can be related to this part of this graph here in terms of size of the pores of the throats. And we can see now, we can see in the lower part here, this figure is showing, of course, a backscattering image, and we have small pores, a shale, a grain of organic matter in the pores formed, isolated pores formed during the evolution of this rock. And now this is the system, the Porous system that we are dealing, are trying to describe and to understand how the fluid interacts with this small classes of porosity, this small example of porosity. And we moved to this part of the graph. Now we are working with very small spaces, voids in the rocks. Of course, technology advanced and offered tools to deal with the problems of how to describe, how to quantify this class of problem in petrophysics. And in relation to carbonates, the advancement of some techniques like micro-CT and other tools that allows us to see, to describe, to quantify these porous systems has improved and become a more and more available force for research and for the academia and for the industry. And here we have some examples like description of the network of pores and involving fractures and of course pores formed by dissolution in carbonates. And now we are reaching an interesting stage where more and more artificial intelligence tools are being used to describe and so the segmentation of the image and the classification and the correlation of the different informations in the pore space are being treated with these tools, which of course will bring more efficiency in the description, in relation, in the estimation of how the fluid will behave in these porous systems. You have different images showing, for example, we will see ahead this rocks. It's laminated limestone. The matrix is very homogeneous, and we will see how this rock is treated as a reservoir, could be treated as a reservoir. And I will discuss an example here. I will bring an example here that we are working with for some years now. And based on this example, I will discuss these 2 points that I think is interesting to bring some research efforts of discussion in discussion. Here we can see what we call an analog of a reservoir. It is laminated limestone. Here in one of the sedimentary basins of Brazil that we used to work with to describe and to produce some scenarios, some models for numerical simulation. This is a compact rock with a medium, not so great porosity, but with no permeability, so it can be treated in the classification of fractured reservoirs as a tight carbonate, a tight fractured carbonate analog. And we have described and worked with this rock as a carbonate, as an analog of a reservoir, because in this region we have good exposures of this rock, and it has a good continuity with some quarries, a few kilometers apart. And the continuity allows us to describe this and to reconstruct some information in the scale of the reservoir scale, and also in the local scale, which we can use to, of course, improve into. And this brings us a question that is the use of a question interesting to think of. That is the use of outcrops as analogs. It's very common now. It's a lot of work developed in outcrops that can be used as a surrogate set of information to build a model that can be used for numerical simulation. That we have, for example, this rock has some physical properties that are similar to some facies of little facies of some reservoirs in the pre-salt interval of southeast basins in Brazil, in the southeast margin of Brazil. And we used to compare, and here we can have access to the surface of the outcrops and describe heterogeneities, discontinuities, fractures, in other characteristics. This analogy can be placed here in this classification of Nelson for fractured reservoirs. We can have a rock that the flow will be developed only in fractures, or we have a transition when the matrix will have some relation with the fractures, and we have the point here where fractures will act in the flow, in the storage of the fluids, and the other end. Now we have, for example, a system with where the fractures will enhance the flow, but they are not the major actor in the flow. And here we have some examples of these outcrops, and we used to call this a 3D outcrop. So we can access faces, different faces of different surface of this exposure, which allows us to describe and to use geophysical equipments and images and imagery of many types of major tools to describe the outcrop and to capture this the different aspects of the rock. To introduce the problem, I will bring the discussion to the discussion. We can see we will follow when we need to describe, for example, together with the engineers, the scale of the problem, the scale of the description we produce and we build for the numerical models. We can see here an aerial view, an aerial photo taken by UAV, and we have a vehicle here for the scale, and we have an exposure and a surface that could be treated in the reservoir scale. We have some hundreds of meters of scale, and we can see some fractures and some faults that cut the rock, and this part, this exposure can be completely described by photos and other kinds of imaging spectral or optical sensors. And in this scale, we use to discretize this kind of structures that will act like corridors of flow for flow. We have now detail of these fractures, and we have that in this scale they are partially filled with calcite that recrystallize that formed after the opening of the fractures. Some of these fractures could be 10 to 20 centimeters or up to 30 meters in centimeters. It's not a fault zone, it's a small fault in the concept of geology. And in this scale, I can discretize, you can put this information in the model. So we will go down the scale, the measure of the scale. And here we can see other classes of fractures, and we have shear fractures and veins of calcites that are open, they are reactivated. And despite the matrix are very compact, we have a large quantity of these structures that cross-cut the rock. And in different scales, we will see bugs and what is a small solution. It can create voids that could be associated with specific embeds in the succession, in the sedimentary succession. And some are reactivated, some are sealed. We have structures formed during the shallow burial, during the deep part of the burial. And we can go down in the scale of description, and we can see now the matrix of this rock. We have this scale here, is small to see, but it is 10 micrometers, and the grains of calcite, of micrite, that compose these rocks is 20 to 15 microns. And we have an example of a plug that we have some small points of the solution. And here we have some micrographs showing microfractures and points of dissolution, isolated points of dissolutions. And so this rock can present up to 12% of porosity. In some cases, 15, 60, 60% of porosity, but there's no permeability. The matrix is very compact, and most of the fractures are sealed by calcite. And if I'm going to treat, I'm going to do with this rock as a reservoir, the tight condition, I will need to go some stimulation, like mechanical or chemical stimulation for interesting production. Of course, we have dissolution structures that call karst, and we have, in this case, we have the rock present a good behavior in terms of karst, because we can have caves with tens to hundreds of meters, of course. And we have some dissolution features in many scales. In some cases, they are connected to the fractures, they are connected to open fractures, they act like buffers of flow during the process of percolation. Some of these structures are, the process of dissolution is increased because they are exposed to the superficial waters. So we need to balance the interpretation of which could be a reservoir condition, or which could be a condition normally exacerbated by the fact that these rocks are exposed in the surface. So this figure, seeing this figure, we can understand the problem. We have a sedimentary succession of a few meters, and so we have vugs and small caves. If we are looking for the meter scale, so if I look for the detail, we can see discontinuity in the interface of the bedding, and as we go down the scale, we can see the connection between fractures and the small channels formed by solutions, isolated pores, the small vugs. And when I'm going to the micrometer scale, we can see that in some cases the matrix will participate in the flow. In some cases, we have open fractures that can be treated as an open conduit And so to integrate all of this information and to understand how each part of the porous system will act is very difficult in many cases, because it can change radically from point to point. In a few meters, we can have radical changes in heterogeneities. So in many cases, we need to think about or to decide what will be neglected, because I can't integrate, of course, all the scales, all the elements of the porous systems or the permeability integration. And I have this figure that we can see in many cases when we are building the models based in outcrops like this. We can see fault zones and fractures, and we have caves, and we have small bugs up to 10 centimeters of size. And we today my colleagues used to to involve some techniques of homogenization, because I can describe all this kind of structures. So I need to use some tool to integrate this in an equivalent medium, to create an equivalent medium where we can mix the information or the permeability that I can have with the fractals, with the matrix. And most of the information we are seeing in this scale for this figure are not involved in the direct building of the model. Of course, we need to recreate these blocks. Of course, it's not in the InterPore scale, it's in the outcrop scale, but you need to treat this problem. And of course, there is many ways to treat that and to deal with that problem. And in some cases, working with superimposed layers of fine grain scale and coarse grain scale, and to getting some mixing in between the phenomena occurring in these scales, in these layers of description. And then dealing with fractal systems, we need to describe and to estimate how many fractals and the classes of fractals families we have in a block in volume. And we use the DFM, the discrete fractal models that is commonly used today for example, in conventional reservoirs, to describe how many fractals in some classes of size I will have in a volume of rock to estimate the effect of these fractals in the permeability. And the great problem, of course, is I have wells with information kilometers apart, and we need to estimate the volume of the quantity of fractals that we have in between these points. And in the case of this outcrop that we have seen, this is a reconstruction. Of course, this is a DFN. This is a model with a distribution of fractal based on the statistical measurements we have in the surfaces of the outcrop. What is in the volume of the outcrop? And in the reservoir, we can have millions of these structures. Of course, it's impossible to discretize or to treat separately any structure. So we use some ways to deal with that homogenization, and we can find some equivalent tensor, permeability tensor for determine the volume of rock, studying the concept of the statistical description of the occurrence. So dealing with these questions, we are building these models and trying to bring the natural information to a realistic model. And I will discuss these questions that are interesting. Now we can see this is very interesting work. We have many good papers dealing with classification of facies, lithophases, and the association of facies, and fractures, and we normally use the description of the density of fractures, the frequency of fractures, the aperture of fractures to describe the volume of fractures in relation to the volume of rock that will be forming the reservoir. And the normal workflow is to describe phases in the succession and to associate the density of fractures or the influence of fractures to that phases, the little phases, because we can distribute this information using seismic data in a reservoir scale model, And the classical understanding of phases includes the information of mineralogical composition, some petrophysics, geomechanics could be mixed, could be integrated to give me a concept of lithophases, but it is basically seated in the description of the rock, like a coarse grain, a coarse sandstone, laminated limestone. And this is what now is the more common application. Today we have a massive use of artificial intelligence tools to not only proceed to classification of automatic classification of phases using, for example, geophysical logs from boreholes, but also the relation in between different parameters like fractures or permeability associated with fractures and lithophases. What we are thinking or what we are trying to do, we have some initiatives in this direction, is now we have the classical interpretation of phases, normally that we can bring this information from the lithologs and the geophysical logs. We have the identification of fractures that also can be executed by automated codes that can be used to the automatic identification and quantification. We have city images, and now we are thinking that using the massive information that now is available about different reservoirs and different rocks, we can put more information like what we can call multiphysics, like thermal properties, electric properties of these rocks, not only considering saturated rocks and fluids, but the mineral matrix, magnetic properties of these rocks, because using artificial intelligence tools and with more information, maybe we can find some classes, some artificial classes that can be used to correlate the information and to enable a better interpretation of how this the porous system will behave in these classes of rocks. So we are arguing that we can evolve to something that we can call it metaphases or artificial classes of these rocks, using the massive information that we have now about the framework of the rock fabric and other aspects, other parameters, physical parameters of rocks. Another question is how we have tested these models. For example, here we have an example that a paper that treated the question of topology of fracture. It's related to the terminations and to the connection of the fractures in a medium, and of course, which influences the flow. And this paper specifically used an artificial example to deal with the process of creating an equivalent permeability tensor, bringing the matrix and the fractals together, or mixing the parameters or the influence of the fractures, an homogenization technique. with vertical and horizontal flow. We can see the examples, and we can find good examples which help us to understand and, of course, to advance in this way of how to integrate fractures in the concept of the unity of a reservoir. The question is, we need to do a lot of assumptions. In this case, we consider the fractures like parallel plates with no hardness in the surface, smooth plates, parallel plates, and the very concept of fractures, as we observed, involves the problem of partial sealing of the fractures, and how they behave when the flow is developed. Like we have geomechanical changes, we have chemical changes in the structure of the rock leading to the solution. And these assumptions normally are not treated because the computational cost. And of course, we need to advance in the question of dealing with this small-scale process. So to deal with this problem of how I can have a real problem with a high detailed discretization of description of the problem that I can bring to a numerical model and to test the information, it's very difficult because, for example, in the case of fractures, hydraulic fracturing, it's of course difficult to make large-scale experiments, simulation in real outcrops, and it involves safety, it involves a lot of logistic problems. And we have good, of course, good examples of projects that tried to execute experimental tests, experimental projects to bring some light in these questions, but they normally are not dealing with the entire model, with the integral model. We have, for example, we can execute tests in blocks of rocks, like hydraulic fracturing. So we can open up this block and we can cut it and observe how the fractures evolve and how the fractures are reactivated. And I can build a numerical model exactly depending on the heterogeneity of this rock. But this is limited in scale, and in the imaging of these structures are normally not so easy to reconstruct. So we are arguing.
Antonio, I'm sorry.
Okay.
Yeah, we just in the interest of time, can you wrap up your talk? Because
okay, I'm finishing.
Okay.
So we are arguing that in some cases we have some examples of outcrops that we can literally slice off bed by bedding and into using new ways of monitoring SIs, monitoring some tests, reconstructed like we slice each part of this outcrop into using imaging and description and geophysical tools to reconstruct integrally the outcrop. It was used like a benchmark that includes the high level of heterogeneity, and we can put these benchmarks as public asset that can be used to test codes and to test numerical simulations that will the way to solve some problems that we have, because some works are dependent on the local features that have in the outcrop. So this is that something we are trying to do, is reconstruct all the outcrop by deconstructing that or by open up of this all the outcrop into turning it into creating a benchmark. Okay, that is the 2 points we have to call. Is we need some benchmarks for testing of codes that deal with fractured systems, and to can apply artificial intelligence tools with new classes of parameters of rocks to create artificial classes that can be correlated with fractured systems. Okay, I want to thank the organization and some colleagues that they have, and I'm very glad to have this talk today, and for the InterPore to have me for this talk today. Thank you.
Thank you, Antonio, for an inspiring presentation. Just to remind you, we have a different format. So we're gonna keep all the questions and discussion at the end of the session. So we move to the next presentation by Professor Paulo Couto from the Federal University of Rio. Paulo, you can share your screen and give your talk.
Yes, I can share, but I think someone else is sharing.
Yeah. Antonio, can you stop your share, please?
Okay, here we go. So can you see my screen?
Yes, Paul.
Yes.
Okay, so let's go. Thank you very much for your attention today. My name is Paulo Couto. I am the coordinator of the Enhanced Oil Recovery Laboratory at the Federal University of Rio de Janeiro. And we're talking a little bit of the use of CO2 injection for enhanced oil recovery and its application in the Brazilian pre-salt. I will focus my presentation on the micro scale phenomena that occurs in the rock. So I'm going to present just a context of the presentation in terms of the Brazilian pre-salt scenario. Then we're going to discuss how to understand the recovery factor of these fields and why this recovery factor is usually low. And then we are talking about CO2 and enhanced oil recovery, how we are doing to enhance production in the Brazilian pre-salt through the use of the WAG technique, water alternating gas. And finally, we'll conclude with some final remarks about this technique. I'd like to start the presentation. I'm sorry, some information are in Portuguese, but I took these from the Petroleum Agency. But this shows clearly the Brazilian post-salt fields. These are the traditional fields that were discovered in the late 70s and the 80s, and they are now entered very clearly into a production decline phase. Okay. So in the last 10 years, more than 34% of production was lost in Campos Basin, and 41 in Santos Basin and Espírito Santo Basin, and in the northeast basins, more than 61% of production lost. On the other hand, we have a huge, a very challenging frontier in front of us in terms of oil production, which is the Brazilian pre-salt. This yellow curve here shows the production of the Brazilian pre-salt, and it's increasing year after year. The last information we have from the Petroleum Agency dates from May 2021, and it shows that the production of the pre-salt represents more than 71% of total oil Brazilian production, with just 125 wells. Okay, so this is total Brazilian production, the green line. The pink line is the post-salt entering into a decline phase, and we have here the post-salt coming up very strong. The blue line is the onshore production, which is pretty much negligible in front of the offshore production. This is reserves, proven reserves in Brazil, presented at the end of, at the beginning of 2019. So we have almost 14 billion barrels to be produced in our fields, okay, and close to 370 billion cubic meters of gas. So there's a lot of oil yet to be produced in Brazil. This is a historic oil production in Brazil since 1953, and we can see here in light green the onshore production, and from the 80s we have an increase in the production because of the shallow water discoveries in Brazil, and now these are shallow waters and post-salt are entering into a decline phase. Later in the late 80s, we went to the deep water post-salt production. And so there was another increase in production. But since we discovered the pre-salt, the production of the post-salt decreases. So in orange here, we can see the post-salt production contribution in the total Brazilian production. And it's very interesting to observe this light orange here. This light orange here is the share of total oil production in Brazil coming from Búzios field. This is just one field contributing with this amount of oil. So what I want to show you with this is that the potential of the pre-salt production is very high. We have wells producing over 50,000 barrels a day, as I'm going to show you later. However, our recovery factor for these fields, it's very low compared to the world average. The recovery factor is the fraction of oil we effectively produce in the surface. We have 100% of oil in subsurface, and we just produced a fraction of it. So right now, Campos Basin, which is the basin that contributes more with the oil production, has produced over 14% of the total oil in place. Okay, and it is expected that Campos Basin will reach a final recovery factor of just 23%. Brazilian final oil and gas recovery factor is estimated to be only 21%. So the recovery factor here in Brazil is very low if we compare to world average, which is 35%. It means we are doing a very bad job here in Brazil. So there's a lot of room to improve the production, not only in the post-salt, but also to increase the pre-salt production. I hope you can see in this table here, it was taken from the Brazilian Petroleum Agency report dated from February 2021, and it shows the production of the first 10 wells, the largest 10 wells in the pre-salt, the largest producers. So Búzios, as you can see, from the first 10, 8 wells are from Búzios, and they are producing something over 33,000 barrels a day up to 51,000 barrels a day. And this is the share of the production on the pre-salt. Búzios is the second, Tupi is the first one, Tupi is Lula. The first well, the first field discovered in the pre-salt is still the largest producer in the Brazilian pre-salt. Búzios is increasing its share in the production very fast, and we can see here the contribution of other fields with Sapinhoá, Jubarte, etc. Okay, and also we have a lot of potential in other fields. We talk about the pre-salt, so we have close to 300 wells in the region of the pre-salt and 14 fields in production. But we still have a lot of areas with no unexplored. We have a lot of areas unexplored. Only 6 to 7% of the sedimentary basins in Brazil were explored. I mean, we don't know if there is oil in the other 94%. I mean, they were not explored. So there's a lot of potential in these areas as well. So we have low estimated recovery factor for Brazilian fields so far, which is close to 21%. But post-salt and post-salt is entering in the production decline phase. However, the pre-salt represents almost 71% of the Brazilian production in May 2021, as we mentioned before. So if we take these numbers and if we increase the recovery factor in just 1%, the Brazilian Petroleum Agency estimates that for this 1%, we will inject $18 billion in new investments in the oil and gas industry. 1% of increase in the recovery factor means an increase in $11 billion in new royalties in the market. And it also means an increase in 2.2 billion barrels of equivalent oil, increase in proven reserves. And right now we are doing this in the pre-salt. We are increasing, or the plan is to increase the production in the pre-salt by the use of CO2, as I will show you later. So we have to make a difference between what we call enhanced oil recovery and improved oil recovery. So enhanced oil recovery is a process that is directly related to the reservoir. So we have primary recovery when we just produce the reservoir with producing wells. We don't inject anything. We just remove mass from the reservoir. If we go for secondary recovery, then we are injecting another fluid in the reservoir with the objective to maintain the mass balance. The most common technique used to do that is water flood, where we inject the production water or seawater into the reservoir with the objective to maintain pressure, maintain the mass balance. When we have EOR, the objective is to increase the production of the reservoir when compared to a primary or secondary recovery processes. Usually EOR or enhanced oil recovery involves complex physical and chemical fluid and rock fluid interaction. I mean, we are acting in the physical chemistry of the fluids and the fluids and the rock. IOR, or improved oil recovery, it's a more extensive process which aims extending oil field lifetime. So IOR involves EOR processes and several other techniques as well: design, well stimulation, production flow conditions, flow elevation, separation process, and several other engineering and management process. So today we are talking about EOR, enhanced oil recovery. I mean, the focus is on the reservoir. So why the recovery factor is so low? Okay, so usually we compare EOR techniques with primary or secondary recovery. As I said, water flooding is currently the preferred recovery techniques for most reservoirs because of the higher sustained oil production rates and the overall higher recovery factors that are obtained compared with the case if water is not injected, I mean primary recovery. If a reservoir falls below the oil bubble point pressure, gas that was initially dissolved in oil will come out of solution, and because of it, because the gas has a much lower viscosity, the gas will flow preferentially to the production well. At the same time, the viscosity of the remaining oil increases, reducing its mobility further. This will reduce the oil production rate further, although it may increase the total production, I mean oil plus gas. Water flooding is relatively cheap especially for offshore fields because of the readily available of seawater, although care has to be taken to ensure that injected water does not result in unwanted adverse reactions in the reservoir. So there must be a compatibility of the injected water with the fluids in the reservoir. In some cases, the injected brines may react with the naturally occurring water in the reservoir to form scale, while injected very pure water rather than brine may result in clay swelling. So the care must be taken with the composition of these water. We can directly associate the recovery factor of such phenomena, of such recovery processes, with a combination of the microscopic sweep efficiency, the macroscopic sweep efficiency, drainage efficiency, and economic efficiency factors. If we consider respectively 80% of efficiency of one of each effects here, we will get a recovery factor of just 41%. So these factors here are directly related to increase the recovery factor of the reservoir. The enhanced oil recovery methods, they act in the microscopic and macroscopic sweep efficiency, while EOR methods can also act with the macroscopic and drainage efficiency. Okay, so the typical microscopic displacement efficiency from a water flood is 70% or less. This is mainly because of ganglia become trapped in the pore space by capillary effects. But the microscopic displacement efficiency is also affected by the relative permeability characteristic of the rock, which control the relative mobility of oil and water when moving through the pore space. The importance of pore scale capillary effects on the displacement can be quantified by the capillary number, where we have V as the interstitial velocity, this is is the fluid viscosity, and divided by the interfacial tension between the displacing and displaced fluids. If the capillary number is less than 10 at -5, flow is dominated by capillary effects. So for typical values of water flooding, we have interstitial velocity far from well in the range of 10 at -5 meters per second. The light oil viscosity at reservoir condition is 10 at -3 Pascal times second. And the IFT between formation water and oil is close to 70 millinewton per meter, which allow us a capillary number of 2.5 times 10 at -7, which is very below the limit I mentioned. So to increase the capillary number, we have to reduce the interfacial tension between the fluids in the reservoir. So in the example above, IFT should be less than 0.1 millinewton per meter to minimize capillary effects. So the rock wettability affects capillary pressure and relative permeability. So we have here an example where we have a very simple example where we have the rock in yellow covered with connate water or formation water in blue, and we have oil. When we inject water, the water has a higher mobility than the oil, so ganglia of oil are still trapped by capillary effects in the pore space. So here we have the final state of this injection where we have the breakthrough of water in this phase here. Okay, and let me just put this pointer, which is better. So when the breakthrough occurs, we still have a lot of water left behind, trapped in the pore space, and this is due to capillary effects occurring in this phenomenon. So usually water wet or oil wet rocks, they result in a high residual oil saturation. So the ideal is to have something like mixed water, a mixed wet rock, where we have something between water and oil wet. So other effects. So now talking about the macroscopic sweep efficiency, the macroscopic sweep efficiency is related to the rock heterogeneities and anisotropies. Professor José Antonio has showed us some pictures of outcrops where we can see clearly how the heterogeneities are present in the reservoir rocks. Although these are outcrops, they are representative of what happens since the surface. And these heterogeneities and anisotropies, they can occur in different field scale. Here we have a plug of rock. This plug has close to 5 centimeters in length and something like 2 inches in diameter. This is the regular size of plug we use in the experiments we could conduct here at the laboratory. This plug was taken from one of these holes you can see here. This is an outcrop in Alagoas, Sergipe-Alagoas Basin. It's a coquina outcrop. I mean, it's a carbonate outcrop where we can have samples to test at the laboratory. And we can see that we have, or geologists that study this area, they identified some very high porosity areas with medium porosity surrounding regions here. So this is heterogeneities and anisotropies occurring in the scale of meters and tenths of meters, and this is in the centimeters or millimeters, and even below this scale. Okay, another factor that affects the sweep efficiency is high absolute permeability layers close to the injection well. So this should be the high permeability layer. So when we inject water preferentially through this high permeability layer, leaving a lot of oil unswept behind. Okay. So the macroscopic sweep efficiency is related directly to the mobility ratio of the fluid. So the mobility ratio is the ratio between the injected fluid mobility and the displaced fluid mobility. The mobility is the ratio between the relative permeability and the viscosity of the fluid. So the higher the viscosity, the lower the mobility. And in reservoir condition, the oil is the fluid that has the largest viscosity. So oil will have always the lowest mobility of all fluids in the reservoir. Some simulations available in the literature when we inject water in the reservoir. Water tends to flow preferentially over oil, leaving a lot of unswept oil behind. Okay. To increase the macroscopic efficiency, we have to minimize the impact of geological heterogeneity. So how to do that is with the viscosification of injected fluids so that you have a more stable displacement front. You can do diversion fluids from higher permeability zone. You can inject a dye fluid in the higher permeability zone. So fluid can be, so the oil can be diverted to lower permeability zones. And we have also to minimize gravitational segregation. When we are talking about gas injection projects. So let's check the use of CO2 to improve oil recovery. But before that, we have just to make some notes about the base case water flood, because when we inject CO2 in the reservoir, the objective is to improve production, but this has a cost, as I'm going to show later. So before doing that, we have to prove that injecting CO2 will increase the production over a base case, and this case is the water flood case or secondary recovery. So this occurs when water is injected in order to maintain pressure in the reservoir. This water flood can be influenced by several factors as a primary production mechanism of the reservoir, if you are producing just because of the expansion of the fluid, or an aquifer acting in the oil zone. Petrophysics properties of rock, of course, this is very important. Properties of injected and the displaced fluids, of course, also very important. Reservoir depth, scheme, and several other factors that could spend a whole day talking about it. On the other hand, extensive knowledge of this technique and fluids is available in the literature because it has been used since the beginning of oil exploration. It has a low cost compared to EOR techniques. And if well designed, it has good microscopic displacement efficiency. The disadvantage is that injected water can cause reservoir damage by scaling or clay swelling. We have low fluid mobility control, which will cause viscous fingering, just like in the simulation picture I showed you before. And of course, water breakthrough is a problem. I mean, when the injected water reaches the production water, water production just skyrocket. And we have to take some measure to reduce this water production. Okay. So miscible gas displacing, the miscible gas injection is the most common EOR technique used in offshore fields. Miscible displacement can be defined as a characterized oil recovery process by the absence of an interfacial tension between the displaced and the displacing fluid. The importance of this process is related to the ability to reduce capillary and interfacial forces that would otherwise cause oil to be retained in the reservoir. The property of fluid responsible for this ability is called miscibility. Two or more fluids are said to be miscible if mixed in any proportion. They produce a homogeneous system that is composed of a single phase. It's more usual for the injected carbon gas to be nearly miscible with oil rather than miscible in first contact. Miscibility then develops between the fluid through the exchange of components, commonly referred to as a multi-contact miscibility, resulting in the gas becoming heavier as it passes through the oil and the oil becoming lighter as the miscibility process occurs. However, even if the gas does not achieve full miscibility with the oil, there are likely to be pore scale displacement benefits compared to a water flood, as gas components may dissolve in the oil, cause its volume to increase. We call oil swelling, and of course the viscosity of the oil will reduce. As a result, it is possible for an immiscible gas flood to result in a lower residual saturation than water oil displacement. So CO2 injection now has been used in the pre-salt as CO2 is miscible in oil at a relatively low pressure. So it's a very interesting EOR fluid. It causes the oil phase to swell, favoring microscopic displacement. On the other hand, it requires a source of CO2 close to the production injection unit. But this is not a problem in the pre-salt. Most of the pre-salt fields, they have a high content of CO2. Also, problems associated with corrosion has to be taken into account, because when we are injecting CO2 in the reservoir, CO2 will combine with water to form carbonic acid. So we will need a special infrastructure, with a special metallurgy to deal with this aggressive fluids combination. And also, if produced together with hydrocarbons, the field process will need CO2 separation units from natural gas to be installed in the production unit. I mean, there's another challenge here where we have to, not only to separate oil from the gas, but we have also to separate CO2 from the produced gas. So this is an example of how CO2 can act in a pre-salt rock. So this was taken from the PhD thesis developed here at the laboratory, where we can see here the contact angle of oil drop in brine system with a rock slab, and we can see this is oil wet system. And when we inject, when we consider the presence of CO2 in thermodynamic equilibrium with the fluids, the system becomes to a more mixed wet system, favoring the recovery factor. The water alternating gas injection is a system that we use the best of both worlds. Okay, we improve microscopic displacement by using gas injection, and we improve macroscopic displacement of water injection. So it uses water injection to control the mobility of phases and control the advance of the fluids. The WAG injection was originally intended as a means to provide mobility control in gas injection projects. The increase in oil recovery obtained with alternated injection happens due to the increase of microscopic sweep efficiency obtained with the gas injection and combined with the improved macroscopic sweep efficiency from the water injection. Besides the advantages related to the mobility control and sweep efficiency, positive results are also related to the reduction of gravity override and improved recovery when miscibility is developed during the process. WAG injection results in a complex saturation pattern because two saturations develops. So the saturation of gas and water will increase and decrease alternatively as we are alternating the injection. This gives special demand for the relative permeability description of the three-phase fluids in the reservoir. I mean, oil, gas, and water. Okay, so this is an example where injecting water alternatively with the gas reduces the volume of gas required to maintain reservoir pressure. Remembering that the gas is very compressible, so if you use only gas, it's hard to maintain pressure. It's hard to maintain the mass balance. It also reduces the tendency of the gas to finger or channel through the oil, as the presence of mobile water in the pore space reduces the gas mobility through relative permeability effects. Vertical sweep efficiency is also improved as water, being heavier than oil, tends to slump towards the bottom of the reservoir, while the gas, being lighter, rises to the top. So WAG is being used in the Brazilian pre-salt scenario as described by Vieira in its paper in 2020. So 3 projects have already started injection: Lula field, Búzios, and Mero, former Libra field. Okay, favorable conditions for WAG happens in the Brazilian pre-salt. We can see here the area of the Brazilian pre-salt and Libra, Mero, Búzios, and Lula field in these large areas here. So conditions are very favorable to WAG using CO2, as these fields, they have a high availability of CO2. They also have a high gas oil ratio, which favors the miscibility of fluids. And also they have relatively low temperature, which ranges from 60 to 80 degrees Celsius. And also they have high pressure. So it favors the miscibility of CO2.
Paulo, In interest of time, can you wrap up your talk in a few minutes, please?
Slide. So just to finish here, to have an example, this is Lula field. If we consider the gas oil ratio and the CO2 content of CO2, we are talking about the production of CO2, only CO2, that may range from 76,000 to 150,000 cubic meters a day. So it's the use of CO2 is an obvious solution for enhanced oil recovery area, as this fluid is already available in there. So this results that were presented by Rosa in the paper of 2018, and this is the first WAG cycle in the pre-salt. We have here water injection period, secondary recovery, and we have here a clear tendency for this recovery. But when we started doing gas injection after the water injection, we can see the production, the rate of oil increasing from this tendency here. Also, we have water production rates during water injection, and when we start WAG injection, water production starts to decrease. So this shows how WAG can help increase the production of this large fields in the pre-salt. Okay, so to conclude, the bottleneck for field scale enhanced oil recovery projects is the lack of reliable mathematical models, especially dedicated for this purpose. We have Professor José Antonio showed how difficult it is to produce a model for a reservoir. And for primary and secondary recovery, you can do a history matching process to increase the accuracy of these models, but we cannot do that for EOR process. So key points for the success of EOR programs are understanding physical and chemistry of the mechanism of each method we are using. And here we dealt with WAG injection. Develop and validate proprietary mathematical models for EOR based on extensive and reliable experimental data. And also development of laboratory infrastructure to support model developments. Also, incorporate new models into commercial simulators, especially for carbonate fields, and characterize the target field, because each field is a different field. WAG may be good for Lula, Mero, and Búzios, but may not for Sapinhoá or other fields in the pre-salt. So each field has a specific characteristic for EOR projects. And we showed here some pilot project developed Lula. Challenges for EOR process in the pre-salt, we could spend the whole day talking about it, but there's a lot of changes related to reservoirs so complex underwater. One of the challenging reactive reservoir with high heterogeneities. It's another challenge, as the carbonates in the pre-salt are highly reactive with injection fluids. Well, I'm running out of time, so I'd like just to thank the sponsors of the research we're doing here at the laboratory. Here are my contacts. If you have any questions, we can discuss after the next presentation. Thank you all very much for your attention. Thank you, Márcio Carvalho. I will stop share here.
Okay, thank you, Paulo, for your talk. Again, we will have a general discussion session at the end of all the talks. So I'll pass the floor to Grigory, who will introduce the next speakers.
Sorry, Hadi, are you there?
Yes, yes.
Oh, hi. So it's my pleasure to announce our next speaker, Hadi Hajimbegi from TU Delft. And Hadi, the floor is yours.
Thank you very much. Do you see the screen?
Yes, perfectly.
Well, perfect. So thanks a lot Gregory. Thank you all for inviting me. It's my pleasure to share the couple of minutes today with you, speaking about simulation of fractured reservoirs, and especially in multi-scale dynamic, multi-scale setting. The work is presented by myself, as Gregory said. My name is Hadi Hajibegi from TU Delft, but also obviously the work is not only my work. Many colleagues and students have contributed, especially our PhD candidate Musa Hosseini, who is going to defend in a couple of months from now, together with Yanio and my colleague at Mathematics Department, Kees Faulk, and our collaborators in Khalifa University in Emirates, United Arab Emirates, Mohammed Kobaisi, and also my former PhD candidate, who is now working for Schlumberger Abingdon Technology Center in UK for intersect simulation development team. And many companies and national science foundations have sponsored the work, so I'm going to just get a kind of an overview of where we stand in terms of the simulation of fractured reservoirs for scalable simulation platforms. So to start the talk, and especially noticing that I am in oil and gas session, I'd like to just remind for a few minutes the audience, especially after the very nice talks that the first talk by Professor Barbosa, and also the second talk as well by Professor Paolo was about the geological characterization of reservoirs, and also especially about the oil and gas production and the need for them. And so let me just remind you all about the scale of the energy that we are consuming in our countries. If for the matter of this conference, we are being virtually hosted in Brazil, although we wanted to be physically there. In Brazil, we are spending about 3,300 terawatt hour of energy in total per year, with CO2 emission of about 400, a bit more, megatons of CO2. Compared to other countries, you can scale where you stand in terms of the CO2 emissions and about the scale of the energy that we would like to have. And one day we would like to turn obviously to sustainable energy and green energy, but to know how facts are and what facts do we have about this important transition, it's good to be reminded about the energy contents of the sources and resources of energy that we have. And to notice that still it's quite difficult to beat 1 barrel of crude oil energy content. And it's very important to compare. It's, for example, if you have geothermal energy resources extracting about 100 degrees of centigrade from 1 barrel, about 160 liters of hot water, it would be about 8% of 1 barrel of oil in terms of energy content. And wind turbines and solar panels obviously also are very, very having quite a challenge for now to be scaled up to become a good portion of energy mix that we need today, and we would need even more tomorrow. Nevertheless, we need to remind ourselves that for the economy that we would like to have, energy is crucially important. And obviously, especially as the previous speaker very beautifully presented, production need at this moment to be very much also centered around CO2 utilization, CO2 capturing and storage, and minimizing of the CO2 emissions. And this is the fact that we have today in the geoscience part, to make sure that we mitigate the emissions, we capture them and store them until we have the time that we can replace energy resources and use those kind of renewable energies for a better society. So until then, we still need to be working pretty much to lower the emission and utilize and capture and store CO2. So with that reminder, when you go to now to geosciences, in which you will have contribution from production of energy, naturally for oil and gas with CCS, or geothermal and new topics, especially on energy storage, compressed air energy storage, hydrogen, aquifer thermal energy storage, and all sorts of larger scale energy storage in which you would target a terawatt hour scale of energy, you would need to really understand and characterize dynamically how the subsurface formation behaves. And that could span from rock salts, solution mine caverns, all the way to porous geological rocks at different depths. And the first speaker, Professor Antonio, Barbosa was presented a very nice geological aspect of this complexity, and it was a great opening to this session as well, and I enjoyed his talk very much. So without too much of a spending on it, we know that many of these reservoirs are fractured, and they are fractured at different resolutions and different scales. Understanding the dynamic of multi-phase flow, transport of mass, heat, and momentum mechanics in these formations is very, very crucial. It is important for our optimization of production, lowering CO2 emissions, also to understand how can we improve the recovery, and also if it is in enhanced geothermal systems as well, if it is in a storage of energy as well, all of them about efficiency, operational conditions, and maintaining the safety. It's extremely important to characterize them and understand them in an accurate manner. Now, coming to these geological formations where they are, you can see also fractures. The reality is that these formations, geological formations are multi-scale by nature. We have a variety of different scales contributing from the scale at which the transport at microchannels take place, all the way to the scale in kilometer at which you would like to decide and operate your formation, your reservoir. Connecting that porous scale physics to that large scale, kilometer scale operational condition is a challenge, and is getting a lot better nowadays than, let's say, 20, 30, 50 years ago, but still a lot of new breakthroughs and innovations are still needed in this geoscience field. We split the physics from porous scale typically to continuum Darcy scale, where we are about a meter, centimeter, and the physics from porous scale analysis bring us with upscale properties like relative permeability, capillary pressure, and other things. And from there on, it's hard to assume scale separation for our parameters, which are extremely heterogeneous. So a very careful multi-scale analysis is required to capture heterogeneity and all the fractures and all the features you might have in order to incorporate them appropriately at the reservoir scale, so you decide appropriately what to do with the reservoir. So here we do multi-scale modeling, in which you are modeling from porous scale to the Darcy scale, and there it's more about multi-scale simulation, homogenization, upscaling, or multi-scale methods in which you can appropriately account for the nonlinear systems that you have with extremely complex heterogeneous coefficients that could also impact a lot the larger scale features that you would observe in the field. Now, if you look into this system, there is one additional challenge that would also make our field a bit different than perhaps aerospace engineering and other engineering sciences. Here, the data that we collect from the system is at different resolution and with different spatial coordinates. We collect low resolution data globally, perhaps high resolution data near the wells. Now, what we have is perhaps in the best case scenario, something I have plotted at the bottom of the figure, but what we want in order to optimize the production or utilize the reservoir accurately and safely, especially, we would like to have a lot more detailed information. So I could, as a simulator person, just simulate and assume I am given all these properties and make the best simulator I can provide with maybe no error for that one realization. But knowing that this is extremely uncertain and I need multiple of these possibilities in order to optimize my field would give a perspective on how to develop a meaningful simulation approach to target these uncertain systems. So former PhD of our group, Rafael Moraes, who was actually employed by Petrobras and now working at Petrobras, did a lot of work on this subject together with my colleague Jan-Dick Jansen. So we started to work on this subject, and it's quite interesting for us also to understand how can we do uncertainty reduction in presence of multi-resolution and multi-scale data and not one scale data, for example. So the multi-scale nature is not only about modeling and simulation, but also about inverse modeling and uncertainty reduction as well. Now with this opening, now let me go to the talk of today, which is about heterogeneities and fractures, and more about a simulation perspective and not even about the entire simulation perspective. Obviously, in this 20 minutes or so, it's just not possible to do any justice in in going through the literature and the state of the art about all the aspects, let me just clarify one thing in this talk and hope that I could get your contribution and questions in the discussion part. At the end of this talk, I'd like to see, is it possible to introduce fractures to the given geological realization that we have from the reservoir with minimum interference in terms of data structure, modeling, and the grades and all the things with the embedded reservoir host rock. Given a reservoir domain with all the great possibilities, injection, production, whatever you have, you would like to insert a lot of fractures and be able to change them easily without too much compromise that would make it unfeasible to do uncertainty assessment, to do optimization, or to enhance your recovery or whatever process you would like to have in the subsurface. So to make it even clear, more clear, I'm speaking about, is it possible that I receive geometries and properties to a fracture generator, a standalone package that would receive these and would let you know the transmissibility list that could be fed into any simulator, any advanced simulator that reads graph-based approach and make it a fractured solver. And this is a kind of a concept that is centered around embedded approach, embedded discretization approach, or from fluid mechanics, immersed boundary methods. And that's the subject of my talk today. So it will be a bit more on modeling and simulation from now on, but it's more about to see, can we create a package like this and be able to connect it so that it is a modular addition of all these complex features called fractures into our given simulator. Yeah. So the reservoir can be heterogeneous as shown in the right plot. It can be anisotropic. It can be anything. It's just the reservoir part. And now I need to put the fractures and look, I want to estimate where the fractures are 2-3 kilometers under the ground. And I should allow for some sort of playing and having a convenient tool in order to play with my system without too much of remeshing and recreation of the discrete system. So with that, I'd like to now set the objectives of this simulation. So I did not talk about unstructured grade development. It's about embedded discrete fracture model. So this is the second approach that you could consider as well. In this simulation framework, we are in the continuum scale, which has heterogeneous reservoir with several fractures. I'd like to have a simulation of strategy that is mass conservative. So it will stay conservative, especially for nonlinear transport systems. It's extremely important to conserve locally fluxes. And it should allow for many fractures, which means that I could have any complex features and I can even play with them a bit. And so to see what would be the impact of this one with the other one and so on, without too much of compromise with the hosting mesh in the reservoir part. It should be also consistent, meaning that naturally in numerical analysis, you would like to decrease your error if your grid space, both in space and time, decrease. It should allow for heterogeneous fractures. Again, the first geological presentation was very, very interesting to show that you could have different sediments, different depositions, and you could have different heterogeneities in the system of fractured reservoirs. And fractures may not be always highly conductive. You could have very tiny features that are barriers to flow. And then you need to also numerically be able to account for them accurately and also in an embedded way. So it's going to be really complicated now. And obviously you would like to be field scale relevant so that you are not just speaking about some tiny models, but you would like to scale it up and in order to analyze a kind of a larger scale systems. Sensitivity analysis is very, very important because we are talking about uncertain systems. At the end of the day, we don't want to simulate one realization, but many, many of them, and collectively connect them with data. So development of forward models obviously need to always consider that we don't look for one perfect solution to a wrong problem. We want an acceptable solution to a possible realization. And we would like to have a black box integration of this in order to allow other simulators or other simulation framework or frameworks to benefit from this embedded approach without compromising too much with their data structure and the way they handle grades or whatever. It would be just a package that would enable you to fractured systems too. Now let me go to the mathematics behind this. How would you allow these fractures to be introduced in a system and account for them even if they are barriers or they are highly conductive without changing the embedded mesh, without changing the matrix rock mesh? Consider a box reservoir here with several grid cells imposed on them. At this moment, don't look into these embedded fractures, just consider the box. We are solving conservation equations, meaning that we are interested to learn about change over time of a quantity psi in our omega-1 in our domain reservoir, net outgoing flux of that quantity, like psi, and then interactions of that medium in terms of mass. For example, if it's for mass transport, there would be mass interaction between that omega-1 with neighboring omegas, the other domains that overlap with you, like omega-2, and that equals the entire source term you have in the system. Classical finite volume-based discretization would start to connect I and J cells here in the matrix with some average mobility, permeability is already there, and then you have interfaces of the grid and divided by delta x. The simplest possible scenario to discretize the capital F here. Capital F would be T, transmissibility, connectivity between node I and J, multiplied by the pressure difference they would have in the mass transport and in the simplest possible scenario. No compressibility, no compositional, no of all these kind of complex systems. Yeah. Now, we add fractures in the system. Embedded approach started by the analogy that the fracture element can be in this system, and we need to interact this fracture element with cell I and J because it overlaps with them. So you would create connectivity between I and F and J with the same similar analogy here. The only difference is that the average properties should be developed between the matrix and the fracture. The distance should be an effective distance between also fracture and the cell. But that was a very successful strategy for highly conductive fractures. When fractures were heterogeneous, that's a Brazilian outcrop I borrowed from our geologists in our department. And here I have a long fracture here, which is barrier to the flow. But when you solve with this embedded approach, this problem, this is the pressure distribution in the reservoir. Here I have pressure high, here I have pressure low. And then I expected that when I have a barrier, I would have a sharp gradient in my pressure profile, but I don't observe that. And this is because the embedded approaches were not able to capture those appropriately. So you always have I and J connectivity, respective of if you have fracture or not. Now with the projection EDFM, we fix this issue. How would that behave so that you can capture all the contrast in the system without changing anything in the matrix mesh, and you would only impose fractures as embedded discrete objects to the system? Here we said, it's not just necessary to see what elements the fracture is overlapping with you. It's important to know the projected area of the fracture to the neighboring interfaces. There you would modify your transmissibilities between I and K, I and J, I and F, F and K and F and J, in order to make sure that the flux that wants to leave this matrix I to go and reach K understands there is a fracture in between. So if you apply that modification, your transmissibility field that will be translated, you are just given a fracture geometry, you know the mesh resolution of your reservoir, you just create all these transmissibility lists, and any simulator can now start to solve the problem. With these projection areas that you would detect where to go, then the EDFM, the original embedded discrete fracture model, which was not able to capture heterogeneous fractured fields, well, now we have with projection EDFM, we can capture it. And it's not just for low or low conductive fractures. For high conductive fractures, the PEDFM would be even more accurate than EDFM, but the difference between the two is much more pronounced if you move forward to heterogeneous fracture properties. And so with this appropriate approach of how to treat the transmissibilities, now you can go and do flow and heat transfer, like in geothermal systems. It's the same. Now transport of mass becomes coupled with transport of heat energy. So you would solve, let's say in this test case, single phase flow with conductive, convective heat transfer and also mass transport as well. And you could have very contrasting properties for your fractures. And again, you are embedding these fractures and using extremely low number of grid cells to capture this system. And then you can go to more complex geometries. Here you need a little bit of geometrical analysis if you want to create that package. So we did that recently. So you can have fractures that can cross over a cone point grid geometry. And there you can add fractures to any given geological field like this and add as many you want, and then get your transmissibility field and then feed it to your simulator and do the simulation with it. And if you want to change one fracture, you change one fracture, it would just change transmissibility field in those elements that it is crossing over and not everywhere else in the reservoir. So it's quite convenient to do a sensitivity analysis too. And now, how would that package work? You have your grid data for your reservoir, you have fracture properties, you know the plates, coordinates or so, you feed it to the PDFM package. The package that now starts to calculate projection areas, distances, average properties, and would send you the list of transmissibilities as if you are one by one adding all these fractures in your system. You want to change one fracture, you change that fracture, nothing else would change. Yeah? And then you can send it to any simulator, anyone we have in-house simulator at TU Delft as well. Both my colleague Dennis Woskov and myself, we are busy with it, but there are more demonstration things. You can have your own simulator and benefit from this package and then do a multi-phase flow and heat transfer in fractured reservoirs. Now you want to change one of these or two of these, you can simply change it. It would just do not much of overhead for you. Yeah. So you can actually use this package if you want. You can contact me and I can send you easily over email or a GitLab address on it. Now, how to do the reservoir scale simulation? Because even if you would characterize, even if geologists would look into it and would say, hey, there are some very significant fractures present in this system, we may want to homogenize the fractures smaller than some certain scales because we can't really afford all fractures to be explicitly present. And not only that, maybe they are not even meaningful to be included, all of them explicitly. So you would approach it like a hierarchical approach in which you would set a fine scale resolution on your geological outcrop or field, homogenize the embedding, the fractures in each grid cell with whatever fractures are there and heterogeneous matrix. You get a heterogeneous realization that can change and you can have different realizations. And some remaining explicit fractures, like these red lines in which you would like to, actually for which you would like to characterize the flow and transport accurately. And you don't want to homogenize them. Yeah, they want to be explicitly present in the system in a dynamic multi-phase flow simulation. Now, how would you approach this problem? You are having coupled system of flow transport, highly heterogeneous system in the background, and some fractures, perhaps many fractures, decided to be explicitly treated. You may want to even cross over the resolution and translate the system into a coarser resolution in order to resolve the computational complexity associated with solving the problem at this resolution. And there again, you may want to go even further than that to do a multi-level, multi-scale simulation, so that you may want to even go adaptively to higher resolutions if you want to, or to lower resolutions if you again want to. So here I'm going to show in a very, very brief manner, how could you possibly do this sort of multi-level dynamic simulation for the processes that take place in fractured reservoirs. You have flow, transport, global unknowns like pressure, local unknowns like saturation transport or heat, convective heat as well. And you want to understand what the process is in your fractured reservoir in a multi-resolution manner. And hopefully you can connect it with data at different resolution when they are provided. So one feature of the method that we have developed is called ADM, Adaptive Dynamic Multi-Level Method. One feature is that you start from your geological realization. It's a heterogeneous geological realization with some explicit fractures there, like the test cases I showed to you before. And now you want to simulate it. This is your fine scale system already. The geology would decide what is your target reservoir simulation scale. From there, now your mathematics helps to coarsen the grid when it is not necessary to capture the process at the fine scale. So you would go and borrow the science from adaptive mesh refinement, turn it around, make it adaptive mesh coarsening, starting from fine scale given by the geology. And now you coarsen it and you go to, let's say here, coarser blocks containing a lot of heterogeneous properties because the transport front is here. So transport will remain in the front at the resolution you want to target. Below, before the front, ahead of the front, you can coarsen it based on your threshold of coarsening and refinement. Now, this is more of adaptive coarsening mesh, not adaptive mesh refinement. And now, together with that, you have global unknowns, pressure, stress field. They are not local. There is no transport, there is no information speed like hyperbolic problem analysis. Here, it's a global system. If you are not correct here in this part of the domain, your pressure will be wrong everywhere because it's a global problem. It's not hyperbolic. It's parabolic if it's compressible. If not incompressible, it will be elliptic. So you do any kind of upscaling in this block, assuming that, well, I'm going to be accurate because my front is far from here. But then you will impact your front speed and front resolution because the pressure, if it's not correctly taken care of here, it would impact the rest of the reservoir too. So there you need to be careful how to transfer your global unknowns like pressure and stress field in the right way to the coarser and finer resolutions. And for that, what we do is we do a multi-scale basis function-based strategy, which actually allows you take your local domain, select your coarse nodes where you want to take to coarse scale. If you take one node in the center, there will be one only representative in the coarser resolution. If you take 5, 2, 3, you have flexibility to decide. And here I am selecting not only at the corners of my grid, but also at the fractures also. And then I compute locally my fractured reservoir system for the pressure to get the local pressure distribution, local. So to use them like my Galerkin shape functions. They are not typical functions from textbooks, but they are computed locally. And now the concept has been also benchmarked with homogenization approach together with Manuela Musa and also Sorin Pope and Mary Wheeler. We did that very recently to check how it would relate with homogenization approach and what is the pros and cons, not for fractured systems, for just heterogeneous systems. Now the two of them together would jointly give you a scalable framework in which you can algebraically translate your system into arbitrary level of final coarse grade. You start from J delta X, which is the black solid line in here, which is the geology reference level, with R and P are mathematics that represent these step 1 and 2. They change the resolution so they allow you go up and down dynamically and fully implicit. You still keep everything coupled and fully implicit. And that's also why you could target complex physics like capillary pressure, hysteresis, and other terms. With these in place, what you would do now is that let's look into some test cases and I'm done. I have a fine scale distribution of pressure for a given fractured reservoir, which is on this heterogeneous domain. There are 20,000 elements here, and I have done only a static multi-scale strategy, computed my local basis functions, and only solved my problem at the coarsest level, only at the coarsest level. Then I used my locally computed basis functions to interpolate, to find out what is the rest of the domain solution looking like. And this is a domain with 86 elements to be solved, and here 20,000. And this is the comparison between the two solution distribution. Coarse grades will happen for fractures and for matrix for both, and not just for domain omega-1, for all omegas, you would coarsen it. With this test, the single phase test, now we go to multi-phase with flow, heat transfer, and other things. Now you can be dynamic, you can capture this very accurately, or you can have a tolerance of saying that what happens if delta T, change of the temperature in this geothermal, for example, application, if the heat temperature difference is above 20 degrees, then you are at the front, or you are very sensitive because the change is quite steep. Then you refine the mesh. If not, or keep it fine. If not, if it's less than 20 degrees that is changing, like here, it's almost changing nothing, then you go to coarsest possible element that you want. But you know that even if you are going to coarse grade here, in this part of the domain, you still will capture heterogeneity and fractures because of these basis functions, so you would not impact the transport due to this inaccurate pressure coupling term. And you can do obviously 3D and complex more physics, but the concept mathematics behind it is just as that slide that I showed to you. The rest is implementation aspect. And so you can do also time stepping with it. It did what I presented was more about spatial discretization resolution change, but you can also transport it such that at the front, you can take multiple smaller time steps and then globally one big march time step. Again, and then again, big march times. So you can do multi-time stepping. That is the work we have done in collaboration with Politecnico Milano on the multi-time stepping scheme for this type of multi-scale strategy. So to come to a conclusion, the embedded discretization approach allows you keep as much as possible your hosting reservoir geological characterization as intact as possible, and add your fracture realizations the way you would like them to be, and would allow any geometrical fractures to be there with any crossing or so without changing of the mesh. And so it allow you to change them, to play with them, change the property of one or so, and be a bit convenient in terms of mesh compromising. We have finished the flow and heat part, and now the package is ready. If anyone wants to use it or play with it, it's most welcome. We are right now working on adding mechanics to this so that fractures and faults these embedded fractures and faults will have mechanical property change too. And after that, after this PEDFM, still a system can be too big. For that, you would like to have a multi-scale strategy to cross over scales, still keep the heterogeneity and the complex coupling terms in dynamic multi-phase flow and heat transfer reserved. And for that, we have developed the ADM, the algebraic or adaptive dynamic multi-scale approach. And the strategy is always about being operational, operator-based and package-based so that you can connect it and benefit from it. And so we look very much forward for collaborations and student projects or so on exploring possibilities to have more advanced simulation capacities for fracture reservoirs. So with that, I would like to thank you once again. I wanted to actually, this is now a new millennia. People like Twitter. And so I had tweeted one statement about reservoir simulation, and I was welcomed so much. So I wanted to bring it in here as well. I think that computational methods for geosciences are more about being approximately right than exactly wrong. It's always an uncertain problem that we are solving, and we should remember that higher accuracy need to be combined with geological uncertainties, and so staying meaningful. Thanks a lot. It was my true pleasure to present today. I wish I was there, and so I would combine it with vacation. But I am on vacation now, but I'm not in Rio, unfortunately. So.
Yeah, thank you very much, Hadi, for your inspiring talk. It was really interesting. I recall everyone that we have a question answer section jointly with a kind of roundtable at the end for all 4 speakers. So Hadi, thank you again for being on time. Pleasure. And well, our next speaker is Yulia Petrova. She's from St. Petersburg State University, and currently she has time in IMPA at Rio de Janeiro. So Hadi, I'm sorry for you. And so Yulia,
we will pay you a visit soon.
So Yulia, the floor is yours.
Thank you very much, Grigori. Well, actually, currently I'm in St. Petersburg, so not so happy. Maybe as if I were in Rio. Yeah, originally I'm from St. Petersburg State University, Faculty of Mathematics and Computer Science, and I have just started my postdoc position at InterPore. And here I would like to present the work with my colleagues from St. Petersburg, Fedor Bakharev, Alexander Yenin, Konstantin Kalinin, Nikita Rastigaev, Sergei Tikhomirov, Dmitry Pavlov, Max Tarkov, Sergei Matvienko, and probably there are even more researchers that I have forgotten, and also the collaborators from Russian petroleum company Gazprom Neft. And so I will talk today about rather specific problem, which is about graded viscosity banks on the rear end of the polymer slug. So maybe brief outline of the talk. So first I will tell about general context that I will talk about chemical enhanced oil recovery methods, especially when we inject polymer slugs, and the viscous fingering phenomenon that appear. The main parameters of this that we will consider are velocity of the pyramixing zones. And but the main part of the talk will be about graded viscosity banks technology, or it's called tapering. I will present the problem statement and results. And if I have time, I would like also to speak about transverse flow equilibrium model that, in my opinion, has potential to mathematically rigorous explain some phenomena which is occurring in viscous fingering phenomenon. Oh yeah, and I have forgotten to say that next year there will be International Congress of Mathematicians in St. Petersburg in July. If you have never been to St. Petersburg, I would say that July is the best month to visit St. Petersburg. So I really very advise this event. So let's start. We consider the following situation. We inject some chemicals, let's say polymers or surfactants. I keep in mind that we inject like acid surfactant, that we do acid surfactant polymer flooding. Here on the picture, the black is there is oil and no polymer, and the white is you start injecting water with polymer, and usually you add polymer such that the viscosity of the polymerized water is greater or equal to the viscosity of oil. That's why you have this stable front propagating of water. And oops, sorry, I'm sorry. Okay. Yes, but usually polymer costs a lot. So at some moment you stop injecting polymer. Okay, let me stop it. And start injecting just water. So water has lower viscosity than polymerized water. That's why the instability occurs. So you have such fingers appearing, which are called viscous fingering phenomenon, and they have really non-trivial behavior. Yeah, so you can see. Okay, you can see that. I'm sorry. It seems that it's not working. Okay, but I won't touch it. So, there is non-trivial behavior, and the fingers are growing faster than the stable front of polymer. So at some time there will be a breakthrough of the polymer fingers into or the water fingers into the polymer slug. When this occurs, so it's considered that the positive effect of the polymer slug decreases. So you don't want this to be occurred. That's why the first very simple natural question is what should be the size of the polymer slug such that the breakthrough occur not earlier than the polymer reaches the production well. I have forgotten to say that this is like very simple model. We consider that the porous media is homogeneous, although I really hope that it will be possible to consider non-homogeneous cases too. And as I have already said, we are considering like a complex chemical enhanced oil recovery procedure such that we already have injected a lot of chemicals, let's say surfactant, so that the most oil that we could extract, we have already extracted. So in some sense, we are already in the situation. So we inject polymer post-flush, and we don't want this polymer post-flush to have a breakthrough with water fingers. So in some sense, the displacement is almost one phase. So let me, so to answer the question that we have posed, what we need is to understand the velocity of the fingers that are occurring here. So let me go to the next slide and introduce the model. We consider the simplest one-phase miscible displacement model, which is usually called the Pisman model. It considers transport equation, incompressibility condition for the velocity, and the Darcy's law. So the main parameter here, which is responsible for viscous fingering, is water viscosity, which depends on the concentration of a polymer. So what is known in the literature about this model? So when viscous fingering appear, so they form what is called a mixing zone. That is the distance between the tip of the fastest finger and the back part of the slowest finger. And what is known about the velocities? So according to the literature, the velocity of the front end of the mixing zone and the rear end of the mixing zone are considered to be constant. Okay, hear me? It seems that I have some technical problems and I'm not sure if you hear me.
Julia, we can hear you.
Okay, thank you, because my screen shows that I'm not in the meeting. Okay.
You're having some trouble. Maybe you can put your camera off. Maybe it will help.
Okay, sure. Let me do it. Okay, so it's considered to be constant. So in time, constant in time, but we need to determine it as a function of viscosity. So how can you determine the velocity of the mixing zones? Well, there are different approaches, like oil field experiments or laboratory tests, but I will focus more on numerical simulation and analytical expressions. So here we have C1 is the polymer and C2 is the concentration of polymer decreased. If you inject water after your polymer slag, then it is just equal to 0. And what analytical models exist? Usually, okay. So usually the empirical models that are very well known in petroleum literature are Koval and Todd-Longstaff models. They represent velocities of the mixing zones being a functions of ratio of viscosities between C1 and C2. And they introduce some effective viscosity, which measures the velocity of the fingers. As far as I know, there is no mathematically rigorous proof of such models or even of linear behavior of the fingers. Even for this very simple model, the closest mathematically rigorous result that I know is about transverse flow equilibrium model, which was first introduced by Felix Otta and Govind Menon for gravity-driven vertical fingers, and then by Yotstas and Salin for horizontal viscosity-driven fingers. So they somehow had an assumption that you have a lot of long, thin fingers, and probably you can assume that the pressure does not depend on the transverse variable. So the pressure depends only on X. If you do so, this model allows you to forget about, let's say, pressure, yes, and define everything explicitly without variable of pressure. And using this model, you can have more or less like rigorous assumptions, rigorous estimates on the velocities of the mixing zones. So they are written here. And I would like to notice that these estimates, they consider not only two concentrations, C1 and C2 of injected polymer and, let's say, water, but they consider that you know the whole viscosity function between C2 and C1. So it's like more integral characteristics. So let me now tell what is the main problem that we considered, and the main, let's say, idea. Yes, it's very simple, but still. So let us. So as we saw, yes. So if the velocity is just a constant, you can calculate very easily the size of one optimal slug, because the velocity is constant, the velocity of the stable front is constant, so it's an easy task. So let's consider, like the picture on the left, that we have calculated some optimal design for one polymer slug. Now, can we reduce the amount of injected polymer such that the effectiveness of such polymer slug is still still the same, but the amount of polymer you use is less compared to one slug? So as it is written on the picture on the right, so it is like the concentration of the polymer on the injection well. So now let's introduce the variable C2 is the second concentration of polymer that we inject. And this idea, yeah, so and you can calculate now the sizes of the slugs, these two consecutive slugs that you need to inject such that the effectiveness is the same. By effectiveness is the same, what I mean is that between every two concentrations, let's say C1 and C2 and C2 and 0, you have mixing zones appearing. So you don't want these mixing zones to intersect with each other. So and the effectiveness, so not losing the effectiveness means that the intersection of these mixing zones, and the breakthrough between these two zones don't happen before the polymer comes to the production well. This idea works. It was introduced by Claridge in 1978, and using like convexity argument, you can easily show that this can be true under some very simple conditions. So the problem statement, yes, is the follows. We want to reduce the amount of injected polymer. Now we consider the injection of consecutive, let's say, n slugs. Yes, so this is the concentration of the polymer on the injection well. And the strategy that we use is graded viscosity banks. So injection of decreasing concentrations of polymer, and between every two concentrations, some mixing zone appears, and we don't want the breakthrough between any of two mixing zones. So we want to calculate the design of such a polymer slug. This is quite simple optimization problem. You can use the following algorithm to solve it. So you can just fix the concentrations C1, C2, etc., and find the times, the optimal times that you need to inject these concentrations. They are defined uniquely if you know the concentrations. Then you can minimize among all concentrations considered here. So the questions that you can consider is, so what happens if you take 2, 3, or 5 slags? So does it give you a lot of, saving a lot of polymer? And one more question is, what happens if we consider taking the number of slugs going to infinity? Will we have some maybe smooth profile of injection or no? So so this is the picture of numerical simulation of 4 slugs that we made in Dumux, and you can see that it's really that the fingers appear, and you can see them here. So about the answers, the results for small number of slugs tell us that if you consider, so these here are results for I think quadratic viscosity function, and we consider different models for mixing zones velocity, transverse flow equilibrium, Todd-Longstaff, and Koval. And you can see that if you take 2 slugs, you have you save around 20 or 30% of the polymer compared to 1 slug. If you take more slugs, you have even more saving, but the numbers stabilize, and in practice it's enough to use 2-3 slugs. So probably it's not, you don't need to inject more slugs. But if you, so on the pictures, you can see the answer, yes, for so the injection schemes, the optimal slugs for 2, 5, or 10, 50, and you can see that if you take 50 slugs, the curve, the optimal design, is very close to some continuous curve, and you can prove a theorem about this. So the theorem is that it doesn't matter which model you consider, the optimal limiting injection profile, yes, is just some function, just a power law function of viscosity with the parameter beta being different for different models. That's a little bit surprising for us because the models, for example, transverse flow equilibrium model seems to be very different from Koval or Todd-Longstaff, but still gives the same optimal design of injection polymer. So let me give some discussions about this theorem. So this is like mathematically rigorous theorem. There are some details, or maybe I should say assumptions, that that I would like to mention. Is that in the theorem there are some assumptions. So it is true not for all viscosity functions, at least for Todd-Longstaff and Koval models. For example, if you take viscosity function being as it is written, so you cannot make even the first step. Yes, so if you consider any concentration C2, you will need more polymer than for 1 slag compared to 1 slag. So it is, so according to Todd-Longstaff model, it is not really have sense. It doesn't have sense to split your 1 slag into 2 slugs. And the thing is that, so as we saw before. So you have some convexity argument, yes, so some functions need to be convex, this to be true. Interestingly, that for transverse flow equilibrium model, you don't have these extra assumptions. So in this sense, we notice that the effectiveness of graded viscosity banks technology is model dependent. Yes, so it's really important which model do you use to calculate the optimal polymer design. And the problem, yes, is that you don't know exactly what is the rule, the law of the velocities of the mixing zones. We made some numerical validation of this technology, let's say, and the simulations were in Dumux with 2 slugs. And previously I was talking that you can take velocities from some analytical models, and here you take velocities from simulations and theoretical. And there are some theoretical assumptions that we wanted to validate through through these simulations. And one of them is what happens to the velocity of the mixing zone in the presence of the other slugs. So does it stay constant, or does it depend on the presence of additional slugs? And as far as we could see, is that it really stays constant. So it's on the left picture here. So there are lines, and they are really very good approximated with lines. So and in the middle, you can see that according to numerical simulations, so it is the volume of injected polymer that you need as a function of the concentration of the second slug. So it's still useful to consider splitting of your 1 slug into 2 slugs. Yes, and 0.6 is an optimal concentration, second optimal concentration for this specific model. That's it. And probably I would also like to tell some words about possible generalization. This model, in some sense, is very naive. Yes, because it talks about polymer, but it doesn't consider, for example, absorption of a polymer. It doesn't consider permeability, that it's not homogeneous, but some random permeability, or maybe even fractures. Yes, so it's about one phase flow, but what happens if the flow is 2-phase? So about the absorption, we have some understanding. It's not very difficult to take into account, because we know how to do it if you consider transverse flow equilibrium model, and it's not clear for covariant length of models. And mainly what adding absorption changes is so the velocities of mixing zones growth will have some additional multipliers before them. So here are these multipliers. They depend on the absorption function and their derivative in the concentration of injected slug. I think I still have some time, maybe not a lot, but a little bit. So I will probably talk about the absorption, how you can take it into consideration, and why these multipliers appear. About permeability, actually, I don't know how to do it. So I really think that there are some works that are related to this effect, and if you know something, that would be really very interesting for me to know. And 2-phase flow, actually, I'm not sure that this simplification that velocities are constant really works, but still there is an idea that you can write pessimistic estimate on the velocity, that is the upper bounds for front velocity and lower bounds for the back velocities. So probably that is all about the graded viscosity banks. But let me tell you a little bit more about transverse flow equilibrium model and how it helps to how it works. Yes, so the main idea, how does it give these pessimistic estimates for mixing zone growth velocities? Because I really consider that it is a very beautiful idea from a mathematical point of view. So we have our Pisman model that we want to treat and want to understand the growth rate of instabilities that occur. And the assumption that Felix Otta and Goenmenan do is considering that the pressure does not depend on the y direction. That is very strong assumption, but when you apply it, you can, using Green theorem, you can calculate the x component of the velocity. And it turns out that the y component of the velocity is not necessarily 0, as you would think from this assumption, but it's some non-zero coefficient. So in some sense, the model, the final formulation of the model contradicts the assumption that it was deduced, but nevertheless, we have a model and we can deal with it. And the hypothesis that I think is true, so at least, well, it's a hypothesis, that this transverse flow equilibrium model always gives pessimistic estimates for velocities of the mixing zone for original Pisman model. But still, you can say, so we have this transverse flow equilibrium model, it's still two-dimensional, it's still very difficult to treat mathematically. What can you do? So the beautiful idea of Otta and Menon says the following. Let's consider two functions, which we will call Cmax and Cmin, which are solutions of one-dimensional equations. And these equations, the coefficients there, are obtained by estimates for the x component of the velocity. So here, probably I should have said before, so the velocity in transverse flow equilibrium model is calculated as you take for any point, you take the mobility function of this point and divide it by the mean value of the mobility in the transverse direction. So this is how the velocity is calculated in transverse flow equilibrium model. And you can estimate it by maximum and minimum value of mobility function. And then you consider these one-dimensional equations. And what is true is that these solutions, these equations, these variables are sub and super solutions to our two-dimensional model. So what I mean is that the maximum principle is true if in the first moment, yes, at time equal to 0, there is an inequality between two-dimensional solution of the TFE model and one-dimensional solution of the introduced model, then it will be for all time. And the same for minimal solution. What this means is that we in some sense have our two-dimensional solution, and also we have, so it turns out that this Cmax and Cmin are solutions to, so are traveling wave solutions. That means that there are two traveling waves, one which goes before the mixing zone and another one which goes after the mixing zone. You can easily calculate their velocities due to Rankine-Guggenheim condition, and you can, so this gives you some estimates for the velocities of the fingers because you know the boundary of your mixing zone. I would like stress that you don't know anything about the mean concentration of your fingers or any exact behavior. You only give some bounds. But using this strategy, yes, you can actually add adsorption or any other effects, probably consider two-dimensional problem. So adding adsorption is very easy because it's very easily added to your model, and you can consider the same maximum principle and also write the estimates for your velocities. So it's not really a problem in the TFIA model. About the conjecture that it's pessimistic, we have tried to check it at least numerically. And what we see is that if you model Pisman model numerically and then compare it to TFIA model, which is here in yellow. So this is the graph of velocity of ratio viscosities. Then you see that the TFIA model is always pessimistic, probably sometimes too pessimistic, but still it works. And we have some idea how to explain why it is so pessimistic. So I think that probably this TFIA model could give some insight into the velocities of the mixing growth, zone growth for the Pisman model. So probably I should finish here, and the conclusions are that so we consider graded viscosity banks technology for polymer injection, and it seems that for standard viscosity functions, it gives so it works. So you can reduce the amount of polymer without losing the effectiveness of your polymer slug. So, but in practice, it's enough to inject like small number of slugs. But the choice of the model for finger velocities is an open problem. So there are no, at least mathematically rigorous results, and probably transfer flow equilibrium model will give some insight about this. So probably I would say some words about possible collaboration. So as I understand, a lot of people here know about laboratory of fluid dynamics at INPA. And so I would like maybe to mention that there is a new initiative, what is called Centro de Projetos de Inovação INPA, that is working with projects, industrial projects. For example, like in September, there will be a workshop for solving these like industrial problems. And I think INPA is very open to any kind of collaboration. So if you have any interest, you can ask questions, or please contact me. And maybe before you ask me some questions, I would like to ask question for you. So it is the symbol of the International Math Congress in St. Petersburg. What mathematical theorem is hidden here? Thank you for your attention.
Well, thank you, Yulia, for a very interesting talk. So our format, we will start a little bit late, but we will start our questions section. So if you want to ask any question, please unmute yourself and ask it, or there is a button below in Zoom reactions, and you can raise your hand, and then we will call you to ask a question. If you have some trouble with sound, you can just type it in chat, and we ask any of our speakers. Or to all of them at once, you choose whom you want to ask. So please, do we have any questions for start?
Grigory, I'll start the discussion.
Okay.
I'll ask Paulo if he can make some comments of the reaction of the CO2 with the carbonates. You touched on that a little bit, but you mentioned already some of the CO2 injection in the pre-salt field. If if there's any issue with the reaction of the CO2 with the carbonates itself, losing injectivity and other problems like that.
That's right. Yes, of course. As I mentioned, each field is a different field, has its own characteristics. We have different rocks, different fluids, and what works for one field may not work for another field. So the example I showed you was, of course, a successful example of CO2 injection in the pre-salt. Actually, it's not pure CO2 that is being injected in these fields. It is a natural gas rich in CO2 stream that is being injected. Because, for example, in Mero, which was the Libra field, the amount of produced gas is very large. The gas oil ratio in Mero is something like 400 units of gas for each unit of oil produced. And from this 400, 44% is CO2. So right now, it's not feasible to separate the CO2 from the natural gas and the FPSO to export the natural gas and inject pure CO2. So what they're doing, they are injecting this stream of gas in the reservoir. So this makes the analysis more complicated technically. So for some fields in the pre-salt, the operators, especially Petrobras and Shell, they are experiencing loss of injectivity in the WAG injectors. We are studying this phenomena, but fundamentally we believe that this is due to hysteresis in the relative permeability curves after banks of water and oil are being injected alternatively. So again, we may experience this phenomena in the injector wells. Of course, there are some other reactions that occurs in the rock, because when you inject a rich CO2 stream, you have carbonate dissolution. These can lead to scales near producer wells where you have a decrease in pressure. Okay, so these are all the challenges that we have to deal with when studying the carbonate rocks. Carbonate rocks are pretty much different than the sands of the pole salt, and there's a long way yet to be run in terms of research.
Okay, thank you. Márcio Murad had his hand raised. Márcio.
Yes, I have a question to Hadi, Professor Hadi.
Yes.
Hi, Hadi, can you hear me?
Yes, Marcio. Hi, good to see you.
Yes, good to see you too. It's a very nice talk. I enjoyed very much. I have been working with DFM, and we started a little bit of EDFM. I am still confused a little bit about your PEDFM. I have here the figure 2 of the paper, which you mentioned, paper by Matthew Tani.
Mm-hmm.
I think you have a similar figure in your slides. Can you share this figure,
Of
please?
course, absolutely. Do you see my screen now?
Yes, right now.
Is that the one
Yes.
you're referring to?
Yes,
Yeah,
yes,
fantastic.
yes,
Let me
exactly.
just then make it full screen so you can. Please,
Okay.
please.
Okay. So this red area, of
Here.
yes, in the classical EDFM model, this was matrix transmissibility, right? So then, when you transfer this area to this projected area of fracture matrix, you are certainly reducing the matrix transmissibility and
Absolutely.
transfer this into a fracture matrix transmissibility, which is non-local because
Absolutely.
yes. So can you comment on that, please? I am
So
still a
this
bit
is thank you very much for this extremely precise and well thought question. There are some absolutely details that Marcio very well known to you as well. In the EDFM approach, when I have a fracture element here, and these are my matrix cells, fracture I and matrix I and fracture F would be connected, and that would be it. K and J would not know there is a fracture in I because it's not neighboring for them. With projection EDFM, we say that it is physical to say that flux from I, in order to reach K, needs to cross over this fracture. And especially if this F is impermeable, it can stop flow from actually reaching I to K with this great cell resolution per se. So you compute the projection interfaces between I and J and I and K and totally delete them, subtract them from I, J, and IK connection. And say, hey, I and K, you are not allowed to independently speak with each other on that projection area. You need to now take the flux from fracture to connect it to K, which is FK, which is this last one. So the same amount of projection area will be assigned to an average mobility between K and F. So you, as you precisely said, you would create non-neighboring connections and would force the flow from I to go to F before reaching K. And then there would be no kind of leakage. With EDFM, you would always connect the two, irrespective of which is in here. I just had a schematic here. So EDFM would connect I and J and would not alter that connectivity, even if you have a fracture in between or you don't have a fracture. And this is exactly where we are standing, that's saying that there will be always a leakage or independent communication between I and J that even if fracture is impermeable wall, still I and J are connected with no modifications. And so that's why we modify the I and J in order to understand that, hey, you are not going to talk directly to each other. And now imagine this graph here. You would have many of these elements set across, along each other. So I and K and I and J in this example would be totally disconnected. They cannot talk to each other at all. Their transmissibility between I and K would be 0, and only fractures can communicate the flux between the cells. So with that, we did also mesh refinement consistency check in that also article. Right now, we just did it for, let's say, more complex geometries like this, because then you need to calculate projection areas in order to disconnect and introduce new neighboring connections, as you precisely said.
I see. Can you also comment on the additional computational costs that you're going to have, because you're going to introduce new? Are they very, very high, or?
That's an excellent comment. I mean, no surprise, of course, but absolutely. I mean, you are going to create not only I and F are connected to each other. Now F and K and F and J are going to be connected. Right. So, but this is necessary for accuracy matter. This is necessary. You need to connect F and K. And what we are gaining is that it's really not really many, but obviously it's given the system, because you have a fracture like that, then or maybe this fracture, for example, it will continue like that. It will overlap K at later stage. So it's not too many interaction zones that you will have, but definitely you are going to allow for more non-neighboring connections naturally. And we have, I cannot really tell you exactly the quantification, but certainly you will increase the connection list and the sparsity of the system, absolutely. It is found to be necessary additional cost because of maintaining the accuracy.
I see. I see.
But that's true, absolutely.
Okay. Okay. Thanks very, very much. It was a
Of
very
course.
interesting talk. We are working on this EDFM models for cars also. No,
Sure.
try to build a EDKM. So I will read the paper and see if we can
It
do
would be
something
our
similar.
pleasure, absolutely, and we could also collaborate as well. Absolutely. Thanks very much for this very.
Okay. Thanks very, very much. Thanks.
Okay, thank you. We have a question in chat from Lucas Pedroni from Petrobras. So greetings, everyone. I would like to know Couto and Petrova views on the relevance of EOR in face of the increasing concerns with climate change and the increasing support and actions to speed up the energy transition. So let us start with Yulia Petrova, just to change the answers.
Yeah, sure.
Yulia?
Well, yeah, thank you for an interesting question. Actually, that is my question too. Yes, I haven't thought about it, so probably I won't be able to give a good answer. So one of the possible directions was mentioned by Paolo about CO2 injection. So it will certainly be have a good impact on climate change. Probably the colleagues could comment even more and better about this topic.
Okay, thank you, Paulo. Paulo, can you add some words?
Well, actually, what we are doing in the pre-salt with the CO2 injection is not considered a carbon sequestration or storage, because the CO2 was already in the reservoir. We bring it to the surface with the production, then we were re-injecting it. But of course, you cannot vent it in the atmosphere, so it's an obvious solution and technically reliable to inject the CO2 with natural gas back into the reservoir. But I have a different view. I have a different point of view than Lucas for the relation between EOR and climate change. The objective of EOR is to increase the oil production, and related to climate change, the problem is how do you use this oil? There's been a natural transition now from fossil fuel to hybrid cars, and probably later to electric cars. So there's a trend to decrease the use of fossil fuels in the day by day. But I think the world will still demand oil. There was a discussion before we started the section today that probably was presented yesterday. I was not able to be here yesterday, but there was a discussion on how Norway is exporting pollution by using electric cars produced in China. So there's a lot of energy needed to produce these batteries and electric cars, and basically the demand for oil will still be high in the world for at least the next 50 years. All the projections, they show this. So I believe EOR will help sustain this demand and take the best profit of the fluids we have underground. But also we have to take care on how to use these fluids. So this is my point of view.
Okay, thank you, Paulo. This is really very interesting discussion. Maybe Hari, you want to add something to that relation EOR and climate change and saving environment?
Absolutely. I mean, I would also continue in the line that Julia and also Paulo mentioned, especially as well, which is about your need for energy is this is mathematics and not much emotion. We need energy to run the society. And now the matter of fact is that it's hard to beat economically, resource-based and whatever with what we have already rely on, and we are developing economies, which is mainly dependent on oil and gas. Now, the responsible utilization would require us to do something with the emission. This is urgent, in my view. We need to work on CO2 sequestration, utilization, and reduce the emission. And in the case we need to emit, and we are just emitting, we need to capture and find solutions to solve that immediately, in my view. And now transition to renewable energies is taking place, is a speeding up, and will also be enhanced and is being enhanced by the economy that is growing because of oil and gas industry as well. So we tax them to benefit the others, and especially the green resources. And so we are scaling up. And as Paolo also mentioned, there are when you look into the food chain, is that they need time to scale up. We need a lot of materials, raw materials, and mining and fabrications and all the kind of industries that are required to be transferred to green-based or sustainable-based resources. So there are so many aspects that we can cover. How do we do now EOR and oil recovery in a responsible manner? Utilize it with CO2 EOR, make a CO2 sequestration to happen, capture it, centralize the emissions, use gas-based when necessary, stop coal actually. And now we have coal, even energy resources in Europe, even. The energy demand is massive. And if you even look into the scale of the storage of energy and then run it based on these, that's why now hydrogen is taking over a lot, especially in Europe, and now also you see in US as well. These are the new solutions that we are finding and we are constantly looking for. But the matter of fact is to live today until we reach tomorrow to a green world, we need to work on this EOR and make it with least possible carbon footprint. And if in the cases of emissions, try to capture it and store it and do something with it. Until the time comes that we can go and produce 3,300 terawatt energy of Brazil with renewable-based energy. It will take time. And it's a matter of fact. I mean, we all need it to be green-based, but it needs time to scale up at this massive scale. It's no joke. It's a lot of energy to produce. 1 square meter of photovoltaic would produce maximum about 200 kilowatt hour. So you would need about 10 of them, solar panels, in your house to supply your year energy. Yeah. And that would be a couple of barrels of oil per year, a couple. Yeah. So it really needs a lot of work and innovation and science to be developed. And InterPore would be the best platform because a lot of them have projections into porous media science, from electrolysis, from carbon sequestration and storage, CO2 EOR, and all the things that we are doing. But the matter of fact is we need to live today to reach tomorrow. And we need a lot of energy today, a lot of energy.
Okay, thank you very much. I would like to add, make a propaganda of yesterday talk. I believe we recorded it. Maybe soon it will be allowed in the internet, because Ali Eftehari showed that with renewable energy, you have a huge gap at night, and it's seasons where it is not wind, and today it's filled with oil. So it's not very clear how to fill this gap in the next years and maybe decades.
I think in that aspect, Gregory, I think we will develop larger scale energy storage. I think it will be in 10 years or so, they will scale up for hydrogen, compressed energy storage, aquifer thermal, and others, they will scale up. I think.
Perfect.
This is
that's a propaganda. Yeah, that's a propaganda of yesterday's talk.
Oh, sure. That's Eftehari's
exactly.
That's exactly the propaganda of yesterday's talk. So please see the videos when they will be allowed. How to say, they'll be on internet. Okay. Do we have another question? I believe Rodrigo, I saw your hand. I'm not sure. You want to ask something?
I have.
Just a little bit, Eduardo. Rodrigo, you have.
Yes, was just to Hadi. Also, I'm not sure if I understood, but if you want to avoid any kind of leakage, if you have a fracture and you want to avoid, at least in the first mesh, the very refined mesh, the fracture has the discretization has to be smaller than the fracture. Yeah, otherwise you're gonna have leakage. Yeah.
Thank you very much, Rodrigo, for the question. The purpose here is that you don't need that refinement. So with this PEDFM, you can avoid that refinement, and any grate block, if you have a sealing fracture fault crossing over, will be disconnected automatically from the neighboring cells. So that cell will be flooded with fluid, but would not transmit fluid to the neighboring cells, because the projection areas that it will have with the neighbors would actually block flow from happening and crossing over. But your resolution would be that if you plot your solution, you will see that there is a grid block with a sealing fault or fracture on it, and it's being flooded, but the flow stops there. So you would see that as if the fracture is overlapping with the grid cell, which is flooded, but that's the end of it. And it would not be able to transfer fluid from the neighbors. That's an excellent point, by the way. So you don't need to refine the grid precisely to just capture that. You can have it big block, and that block would be the only block that will be flooded, and neighbors would stop. Now you want to capture it more accurately, you would refine, but you know that that would be the end block, that end, and then connection with the neighbors is going to be just simply 0.
Okay, thanks.
Thanks a
Okay,
lot for the
thank you.
question.
Next question is Eduardo and then Anderson. Eduardo, please.
Okay, first, I'd like to make a general comments, and I would like to thank all the speakers for the excellent presentation, very clear. All the presentation included a general overview of the area and also highlighting the challenges underlying still open problems. We from the Brazil InterPore chapter really thanks all the speakers, Professor Jose, Julia, Paulo, Hadi, as well, for the kind attention along with possibility of career research topics for the younger researcher here in Brazil. And so my question is to Hadi, Professor Hadi, and more maybe a curiosity related to the local reservoir information for construction of the transmissibility and the CFL stability condition. I think it's your slide 14, maybe it helps. How the information from the hyperbolic flux enters in the transmissibility. I mean, could you please?
Of course. No, absolutely. Thanks a lot for the question. Absolutely. There are two things in here. And thank you very much for that.
Because just to add more information about my concern, thanks, Hadi, because in your case, the hyperbolic fluxes F is discontinuous, right? And there is no theory about this for system. So no eigenvalues available, even approximate. And the fractional flow functions appear in that are discontinuous, actually.
Sure.
So my curiosity is how do you handle this very tricky situation to evolve in time to the calculation of the time steps? That's it.
Absolutely. Thanks a lot. Thank you very much. I mainly focused here in spatial great resolution and less on a stability and transport in time. And this is an extremely also valuable question and a contribution. Thank you very much for this very nice question. So what we do typically is that I just try to simplify here to transfer the message here. There is a transmissibility that would approximate your flux, and it would be a discretization of lambda grad p, and not fractional flow times velocity. It will be lambda grad p, which would be then in front of a divergence operator that would be more of an elliptic operator. Now here, what you would do is you would do permeability, absolute permeability of the reservoir with harmonic average, fluid properties based on upwind scheme to preserve the stability. And then this is how we use that typically, and everybody else also as well, that at the interface, fluid properties will be upwind based and the rock properties would be harmonic average based. Now the selection of time comes in. There are two restrictions for selection of time. One is about stability preserving and being able to allow for large time steps. Another is about the quality and impact of the selection of the delta T in your results. One restriction is coming from the CFL number, that if you select based on an explicit time integration approach, then you need to characterize your delta T to be below the delta X divided by the wavelength or the characteristic speed in the maximum characteristic speed in your domain to keep the entire domain stable. What we follow in order to avoid that restriction is an implicit time integration, which would then allow us not explicit, but then implicit. So for linear systems, additionally stable. However, because we are talking about nonlinear transport problems, again, our linearization scheme through Newton lemma and then iteratively solving for the next time step could be impacted by the amount of delta t we take in the domain. And the remedies for that is that you have some sort of flux corrections, inflection point detection and correction in order to guarantee your nonlinear time integration scheme, which is based on Newton lemma usually, would always converge and would give you your n+1 state of the system. For that, if you have a linear or convex fluxes, you are always good. Your Newton will converge. But if you have presence of capillary pressure, especially, or contact current flows of gravitational things, gas wants to rise, but liquid wants to come down, and they will have different characteristic signs in the interfaces, then you will face into some problems with the convergence of your Newton. And there are so many methods like trust-based Newton approach and other approaches that would fix your Newton iteration scheme to help it converge to a state. And there, now following implicit time integration, you can relax CFL in general. You can go for CFL 10, 15, because you want to just march faster in time. Now you can converge. And now the next question is how accurate the solution will be, because you will be first order accurate in time because of first order time, upwinding scheme. Unless you do TBD and higher order methods, with the classical approaches, you would be just first order upwind based would be just first order accurate. Yeah. For explicit time integrations, absolutely, you check CFL, make sure you are in a stable zone. For implicit schemes, you will be able, in principle, to take any delta t and converge, but because we are working with nonlinear fluxes, we have a lot of corrections to the iterations of the Newton loop to make it converge all the time. Properties at the interfaces will be upwind for fluid transport and heat transport, and for rock properties and fracture properties, and so will be harmonic average. And with these, we carry on the simulations in time. And one last piece of thing that I wanted to highlight here is that in this test case, I will like to just zoom it a bit further. Here, the situation is that you could take any delta t and converge, but the problem is you would be inaccurate. And then you need to have an accuracy measure that, especially if you have, let's say, reactive transport or some stuff that the gradient and the properties at the front is very important for you to be accurate and take it accounted. So here what we are doing is that we will march, with delta t, smaller delta t here. So we calculate CFL number across the entire reservoir. Detect where we are really, in terms of the characteristic speed, we are really marching quite big with delta t. Here, then the front will be detected. The red zone here, the red cells, are going to be taking a small delta t, like 10 time steps. Then the whole domain will go one large time step. So you do one big time step, and then you do smaller cuts in the front region. And you make it such that you preserve mass conservation. So you strict it to be mass conservative. And then you will simulate with a multi-time step to make sure you stay not only stable and convergent, but also accurate. And don't take all the big delta t, because you can take delta t to be big because you're doing implicit time integration, but also the front is taken sharp and accurate. So this is what we do in practice.
Okay, Hadi. Many thanks for your talk. I really like it a lot. I have some interest in these hyperbolic problems since the theory is open, completely open, and develop of new numerical schemes that is convergent and accurate is really hard, because the theory for a system that does not exist.
I fully
the issue of convergence is really an issue. So many thanks.
I fully agree. No, absolutely. I mean, it has been I did my PhD in ETH. Randall Lebeck's lecture notes in ETH on hyperbolic problems were half of the exam we did in that course long ago. as half of the participants, I guess, were not born in that. But at the same time, it's complex, but very entertaining and very nice. I mean, they are really a good part of the problem, the hyperbolic problems.
Okay, many thanks.
Thanks a lot for sharing.
Okay, thank you. Anderson, do you want to make a question?
Yes, it's sort of a comment towards a question for Hadi. I'm just wondering, because as far as understood, the way you're doing the simulations and the way you're implementing fractures, you can assign any arbitrary shapes for the fractures. Is that true? So that you could incorporate other geophysical observables to the size and shapes of your fractures. Is that correct? Because if that's the case, that's very neat, I would say.
Well, I need to read Mr. Anderson. Thanks a lot for asking this question. The implementation part, the implementation that we have done are those that I have shown today. Your fractures should be planar, rectangular in our implementation. And it's because Musa is now graduating and we have plans to make them ellipsoids or with different geometries. But for now, what we have is that you can have a plate that can have any orientation in 3D and in any configuration. And it can cross over any other objects of any other fractures too. And that's the code is open source and we can send it to whoever likes to use it as well.
And the interesting thing, if you can assign any shape, is just put it 0, whatever the fracture is not there. It's a planar structure with 0. You can have even a kind of...
You deactivate the fracture. This is what you mean.
Deactivate the fracture at some point.
Yes,
because if you do this, then you can assign any shape to it. Any actual active
well, if you
shape
can decompose the shape into rectangular plates for now, so if you have a fracture that is non-planar, then you can decompose it into plates that are conforming them each other. Absolutely, these are the things that you can do now. Yeah, but if you really want to have this, and by the way, the connection with the geophysics part as well. This is an ongoing project I have with my geophysics colleagues in order to couple what will be the dynamic in the reservoir and how can it be observed through seismic. And what would be the sensitive and that absolutely right.
That was going to be the next question, but you already answered because
no, please,
I'm a geophysicist myself, so I was interested in that. It's very interesting.
No, I'm pleased to hearing that, but it's absolutely right. As I said, the data that we get would decide what is it observable, and then what can be modeled, and especially dynamic change in the reservoir. How much of it can be observed in the field? And so we collect the data that in the field. So what we are doing is we do reservoir simulation part and then do seismic as well and see how change of the dynamic in the reservoir can be seen by the different frequencies of the seismic surveys, for example. But it's an ongoing research and we are thinking about this. And we have a joint PhD student with my colleague, Kees Wapenaar, who is a physicist.
Yeah, he is.
So we are at this moment, as I'm talking, we have a joint PhD student who are working, and if you are interested, we would be delighted to speak with you about this.
Yes, I have some ideas on that, so we could share those. Thank you.
Thanks a lot for the well thought question.
Okay, thank you very much. Do we have more questions? Well, Hadi, just to complement the other questions, that is apparently there is no one in the queue. I didn't study a lot about this ADFM, but as I understood, your model of fractures, they are one-dimensional, so they are very infinitely thin and as long as you want, planar. So the question is, physically it has some thickness. It doesn't matter do you think from physical point of view, it doesn't matter? It doesn't impact anything? I'm sorry for naive.
No, that's a great mathematical question, and I'm not surprised by a mathematician to be asked. You also targeted a good point for the EDFM methods to stay consistent, and the formulation stays valid. you need to assume that the fractures live in one lower dimensional space compared to the embedded rock. So if you have a 3D geometry, your fractures are 2D plates. Now you virtually assign aperture to them, but that aperture stays quite small compared to the matrix grid size. This would be then in a way, philosophical validation framework for the discrete fracture modeling approach, in a way that you are modeling the fractures as lower dimensional manifolds or spaces. And you virtually assign aperture to them, assuming that the aperture size is so small compared to the grid space that you have, that you can really assume it is actually a formulation in 2D domain compared to 3D in your general matrix rock. How would that impact? You will assign aperture, would also introduce your conductivity. If you see open slit, like parallel flow, Poisson flow, the aperture change would change your permeability or conductivity in the fracture, but you can have rough fractures, or what Professor Barbosa presented, you can have sediments inside the fractures, they can be sealing, they can be heterogeneous and more complex than just simply parallel flow plates. There you assign a permeability or conductivity to them with a given aperture, and sometimes maybe porosity even, or maybe not just aperture, to know what's the volume of that element, which is a 2D element. If it's a plate, there will be a plate like this, but it will be so thin that you have an aperture there, and compared to the entire grid block, it will be very small. And then we do all this kind of change of the aperture with respect to pore pressure change to include geomechanics, or if it is fault, to do some friction law and friction coefficient. Now, if you refine your grid so much that the aperture is comparable to your grid cell, then it is not an embedded question. That's your. Then it is, okay. I know where you're heading to. It's a very good point.
Okay.
It's an excellent point. In my view, EDFM or discrete fracture modeling should not work in terms of philosophy, because this is not a lower dimensional object any longer. It has a 3D element assigned to it. Now it will be purely like immersed boundary method in fluid mechanics. You have a 3D object imposed on your 3D object. So then you will just introduce interface communication with them. If it is impermeable or permeable, you would do exactly what immersed boundary Peskin, and so it's quite a rich literature in fluid mechanics on immersed boundary methods. Mm-hmm. The complexity of what we have is that when the fracture is so thin, so it becomes lower dimensional space, how would you consider them? And that's now solved. Otherwise, if it's 3D object within another 3D object, you need to discretize the interface and allow for some communication between them. Either they are porous, so they accept velocity exchange, or maybe not. And then that would be it.
Okay, thank you very much. I think we are coming a little bit late because our next section will start at 1:15, right, Marcio?
Yeah, so the actual talk starts at 1:30, yeah, and we open the room at 1:15.
Okay.
For some initial words, and just to remind everyone that it's a different link for each section, so it's a different link for the afternoon. You all received the link through by email.
Okay, that's it. So we would like to, in the name of all organizers, I would like to thank all the speakers again. Thank you to share your knowledge with us. Well, and see you afternoon, hopefully.
Okay, thank you.
Yeah. Thank you. See you.
Thank you all. Thank you, Haji.
Thank you. Bye-bye.
Thank you.
Thank you.
Bye-bye.
Next time, hopefully in Brazil. Yeah, okay.
Many thanks, Haji. Many thanks.
No,
My pleasure.